Hello, everyone, and welcome to today's The Scientist Symposium. I'm Deanna McNeil, Assistant Science Editor for The Scientist, and I will be moderating our discussion. Today, our expert panel will highlight the conditions that make a pathogen more likely to cause a pandemic, what precautions can be taken from scientific, diagnostic, and therapeutic perspectives, and the role of public health in pandemic preparedness. Before we begin, I'd like to thank Sinobiological and ACRO Biosystems for sponsoring today's webinar. We like our symposia to be interactive. We encourage you to send us your questions or comments at any point, and our panel will address these during the Q&A session following the presentations. To ask a question, simply click on the Q&A tab and type your query into the question box located on the right side of your screen. Our sponsors have provided us with some helpful resources related to today's webinar, and we have posted these in our handout section on the right side of your screen. You can access and download these documents at any time during the webinar. And if you have minimized the Q&A panel, simply click on the blue chat button in the bottom right corner to bring it back. This symposium will be archived on the Scientist website, and we will send you the link via email within a couple of days. Please note that you will not be able to download the presentation slides. And with that, let me introduce our first speaker. Jason Kindrachuk is an assistant professor in medical microbiology and infectious diseases at the University of Manitoba and Canada Research Chair in molecular pathogenesis of emerging viruses. He completed his undergraduate and graduate work at the University of Saskatchewan and held postdoctoral fellowships at the University of British Columbia and NIH, where he also held multiple senior research scientist positions. Kindrachuk's research expertise and experiences have focused on emerging virus pathogenesis and outbreak preparedness with a focus on low and middle income countries, including outreach activities in Sierra Leone, Gabon, and Kenya. He has served on multiple national and international expert committees and working groups on emerging viruses, including the World Health Organization. He is active in international outbreak response efforts, including the West African Ebola virus disease epidemic, and most recently, COVID-19. Kindrachuk's current research focuses on the circulation, transmission, and pathogenesis of emerging viruses that pose the greatest threat to global human and animal health. So we can make sure that your slides are up and running, Dr. Kindrachuk.
You got it. Perfect. And I'm just going to switch to this. And okay, right. Hopefully we're all good to go now. On my side.
Take it away. Yeah,
great. Thanks so much. And it's funny, the difference a few weeks can make. I've actually finally moved up to associate professor, so that's always kind of a nice bonus in academia. And listen, I will say right up front, me going first in this presentation today amongst all these great speakers is kind of like opening up for the Rolling Stones a bit, right? So you're super excited, but at the same time you realize that the real expertise is going to be coming a little bit down the line, and people just want to kind of get through yours to get to their talks. So, really, I want to talk a little bit about some of the work that I've been doing and have done in emerging viruses, and in particular, emerging zoonotic viruses, and this whole idea of preparation and response, and where do we need to actually be kind of focusing resources. And the first thing I will come off to say is, I do want to appreciate, here at the University of Manitoba, our campuses are located on the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene people, and as well, we're on the homeland of the Métis Nation. So certainly want to appreciate that territorial land acknowledgement. And I always kind of start these talks, kind of reflecting back on my days at NIH. Listen, I was very, very fortunate to have spent some time actually holding space beside Dr. David Morin's my last few years at NIH, and really got to kind of pick his brain a little bit about emerging viruses and kind of perspectives on emerging viruses and where we kind of sit in this fight against emerging infectious diseases as a whole. And if we look at this, this beautiful diagram that he and Dr. Tony Fauci had put together in 2020 and published, what we can see is that, listen, we are constantly facing either new emerging viruses, re-emerging viruses and infectious diseases, or those that are potentially deliberately emerging as well, right? And I think what I want people to kind of appreciate is that, when we are facing new disease outbreaks, or whether we're thinking about COVID-19 or we're thinking about monkeypox virus, or certainly even Sudan virus and Marburg virus, the past over the past 12 months, we have to appreciate that these are not events that occur in isolation, that these are just adding to the cadre of other infectious diseases that we're facing. And if we simply look at the timeline of new emerging infections since 1998, what we can appreciate is that there is an increasing frequency of these events that are occurring. And realistically, we are not going to be able to defeat all of these different emerging pathogens that we're facing. Really, it comes down to a battle of trench warfare in many cases, and trying to just stop these viruses from making up any additional ground. And I think the last 3 years have certainly highlighted the real fight that we are in. Now, where I work is really at this intersection between wildlife and animals and humans. And when I say that, I should say non-human animals. Emerging zoonotic viruses are those viruses that and diseases that naturally move between animals and humans, and can actually go in both directions. What we need to appreciate is about 60 to 70% of all of the global emerging infectious diseases that we are facing are zoonotic in nature. And certainly these diseases have massive impacts on not only human and animal health, but also massive economic implications. And simply, if we think about going back 20 years to the SARS epidemic in the early 2000s, here in Canada, we had a pretty big instance of cases in the eastern part of the country. We didn't have any fatalities that are associated with that, but we did have a massive economic impact. And certainly, I think it changed the face of public health in Canada moving forward. If we look at the West African Ebola virus disease epidemic, while that epidemic was largely limited to West African region or West African nations in Africa, that epidemic cost about $53 billion to try and get contained. And obviously, we still see impacts of that disease today, and I'll talk a little bit about that. COVID-19, we know the estimates are in trillions of dollars at this point, and will continue to increase as the months and years move forward. But then we also need to appreciate the impacts of the expansion of H5N1 circulation over the past few years, in particular, the economic impacts and food security impacts that we face with that, even without strong incidents of spillover into humans. And of course, in the background, we have to appreciate that the global environment is also changing. So not only are we, seeing this increasing frequency of emerging infectious diseases, but we're also seeing global changes, particularly in climate, that are exacerbating some of these events. And this is a beautiful diagram that Dr. Ian McKay put together in 2018. I was very fortunate to be able to talk and help Ian a little bit on putting this together. But I think it's very, very important. And I think when we think about this idea of climate change, we tend to just talk about it, in terms of the direct human cost, but not necessarily thinking about the secondary impacts of climate change on emerging viruses, and certainly geographic ranges of emerging viruses. We can appreciate that the effects of climate change can have certainly big impacts on things like reservoirs for viruses, the spread of vectors in particular for vector-borne diseases. They can have impacts on transmission for different viruses, in particular with changes in droplets and droplet sizes that can have an impact on the ability of these viruses to transmit. But I think we also need to appreciate certainly the potential impact on reservoir migration and geographic changes in the organisms that carry these viruses. That includes, obviously, insects, but also if we think about things like bats or rodents. we have to appreciate that increased expansiveness of those geographic ranges for those hosts can take those viruses into different and new geographic niches where we may see potential explosive increase in virus circulation. And of course, we have to appreciate, listen, none of this is new. We're talking about preparedness. And this didn't just come out of COVID, this idea that, oh, we need to, invest in better defense systems and early warning systems and surveillance systems. We've been talking about this for decades now. And I think it's really important to highlight that fact that I think there's been some progress that's been made, but I think in many cases, this idea of truly investing in emerging events that we can't necessarily predict when they're going to happen has actually not been, I think, taken completely seriously across the globe by those that have the means to be able to invest. Certainly, if we look at the Global Preparedness Monitoring Board, their release in September of 2019, looking at urgent actions to prepare for large-scale public health emergencies. If we look at just 4 of the points that they highlighted, we can see where we I think failed considerably with COVID-19. First of all, heads of government had to commit and invest. Here in Canada, we are still fighting by tooth and nail as an academic community and as a public health community to get increased investment in not only basic or fundamental research, but also preparedness, in particular within the global south, appreciating that, we could, because of globalization, we can no longer consider ourselves as an isolated nation that, that has that, that defense system that we had maybe in the early 20th century. We need countries and regional organizations to lead by example. I don't think there's any question when we look at COVID that this was one of the failures that happened. We didn't necessarily have countries that stood up and led and said, this is what we need to do, and we're going to invest and set the precedent. We need all countries to build strong systems and invest in strong systems. So not only do we need to build national surveillance systems, but to be fair, we know where the highest potential of emerging virus spillover is going to occur. We know where those global hotspots are, where they tend to be. We need to start to invest in infrastructure and surveillance systems within those regions if we're truly interested in early detection systems. And of course, we need countries, donors, and institutions to prepare for the worst. COVID-19 has been bad, certainly. Can talk a lot about how it compares to 1918 and to other pandemics and epidemics. But I think we have to appreciate that we can't assume that this was the worst case scenario. We have to look at this as certainly a learning exercise as well, from where we have gaps and where we need to continue to invest. And certainly we can appreciate that we have priority pathogens that we have been focusing on for a number of years for vaccine development and surveillance development, including disease X. But I would also highlight that, to be fair, orthopox viruses were not included on the list. And in 2022, we saw rapid global expansion of monkeypox virus, which we had not seen before. So we need to certainly be adaptable for this. And really where I want to focus is to the viruses that I've worked on and continue to work on as kind of case studies for where I think we need to be better prepared. Ebola viruses are what got me into research in the first place. I always credit Dr. Peter Jarling from the hot zone, coming out of high school into university. That kind of set me on my way. And certainly Dustin Hoffman's now somewhat comedic take as a virologist in outbreak certainly pushed many virologists to move into high containment research during that time period. But Ebola viruses belong to the family Filoviridae and actually are a genus of 6 different species of viruses. They were first identified in 1976. This included Zaire Ebola virus, or what we now know as EBOV for short, and Sudan Ebola virus, or SUDV. And Ebola viruses tend to have high case fatality rates in either humans or non-human primates. And those range typically from 40 to 60%, in particular for EBOV. Here's a picture here of Ebola virus stained in blue emerging from an infected vero cell. It's taken by John Birnbaum when I was still working with NIAID. And this, of course, is Dr. Fred Murphy's most famous Ebola picture that we've ever seen, and continues to get circulated of what Ebola truly looks like. Now, what I want to highlight is, I talk a lot about the West African epidemic, but what we need to appreciate is that epidemic ended in 2016. From 2016 onwards, we've seen really nearly an annual, if not a biannual, reemergence of Ebola virus certainly in sub-Saharan Africa, primarily in the Democratic Republic of Congo. So while we have a vaccine and while we have good diagnostics, and we have certainly better readiness and preparedness for Ebola virus outbreaks, they continue to increase in frequency, not to the same breadth as what we saw clearly in West Africa in 2014, but they continue to be public health threats. And we need to appreciate that our preparedness and response efforts can't only focus on the point where we start to identify human cases, but certainly trying to understand where Ebola viruses are spilling over from nature, whether that's direct contact with what we believe to be the reservoir host in bats, or with infected intermediate hosts, either non-human primates or other animals. We also need to appreciate that there's a post-outbreak response and preparedness that we need to appreciate as well. That includes the potential for long-term health impacts in Ebola virus disease survivors, but as well persistence in Ebola virus disease survivors that may not be recognized by traditional blood-based diagnostics and can lead to the eruption of new transmission cases. So, we focus on this idea here of outbreak, but we need to be thinking about pre and post-outbreak as well in terms of preparedness. And I think we do need to also appreciate kind of this delineation of what research containment looks like versus outbreak response. And I'll use kind of my own personal experience as an example. Here is the BSL-4 facility that I used to work at in Frederick, Maryland. This is me the day before I deployed out to Liberia in 2014. So here I am working on Ebola virus in Vero cells. This is Pete Jarling here showing our positive pressure suits that we use. So you get a sense of what containment looks like, right? Well, this is what containment looked like in Liberia from an outbreak response standpoint. This is an old malaria diagnostics facility. This hallway in the mechanical room actually had a bat roost inside that mechanical room. So we would often come in the morning to find bats all over these glass doors. And the concerning part about that is that those glass doors lead into the lab space that we had retrofitted to be able to do all of our diagnostics. Here's one of my colleagues from the US as we're starting to work on Ebola virus samples from different patients. So as you can see, we're wearing here our Tyvek suits, but this is just a regular space, right? This is not a BSL-4. So there's a practicality issue that we need to appreciate, which is, we have to think about biosafety for research containment. There's no debate. We also have to think about the practical aspects of outbreak response. How can we respond? And I would posit that, in the 4 weeks that I was there, we blasted through, I think, about 1,600 samples, and we were running operations, basically 8 a.m. to 9 p.m. Monday through Sunday. So when these operations are up and running, our primary goal is to get through as many samples as we can to be able to identify those cases as early as possible. And of course, we need to appreciate too that listen, this is not only about diagnostic and certainly infrastructure preparedness from a laboratory or a diagnostic standpoint, but also from a healthcare access standpoint. I was very fortunate to be able to gain be at National Institutes of Health when NIH was caring for Ebola virus disease patients. The Special Clinical Studies Unit at the Clinical Center of NIH through Critical Care Medicine, where I was a staff scientist, cared for 3 different Ebola patients. This is our 3rd patient, which was in March of 2015. Primary care was provided by Dr. Dan Chertow. And this graph basically provides an overview of their viral load here in black. So peaking out at around day 9, day 10, then dropping off prior to their release from the hospital. But what we can also see in orange and across the top axis is the increase in their disease severity. So what we can appreciate is, first of all, you don't just continue to see increasing amounts of virus, and that leads or correlates with increasing tissue damage. What we actually see is that there's a tipping point where the virus reaches a peak and drops off, but that tissue damage continues to increase. So, this really kind of gets back to this idea of, you're trying to battle the virus, but you're also trying to battle the over-exacerbation of inflammatory responses and the immune system of the patient. And that can kind of pivot where you're focusing on from a patient care standpoint. This patient was also provided with mechanical ventilation because they went into respiratory failure, and were vented for 9 days. They also provided fluid replacement therapies, and additional therapeutics, though they didn't have any experimental therapeutics that were provided. And the reason that I bring this up is that this patient ultimately recovered. And what we can appreciate is, if we look at case fatality rates, those that were able to get advanced care as compared to basic care like we would see in the field, their case fatality rates dropped pretty significantly, right? So just being able to provide patients with good access to healthcare infrastructure really can bring down the worst aspects of this disease. People still got sick, there's no question. But I think it's very, very important to highlight that that in these cases, you're able to at least control the disease and help with recovery. And of course, we know that vaccination efforts have clearly been important to be able to try and reduce the number of ongoing cases and the length of outbreaks that we've seen. Now, there's another aspect too, which is, when I talk about healthcare infrastructure, it's not only the ability to care for patients that have Ebola virus disease, but also to be able to provide care for patients that have other healthcare needs beyond Ebola virus disease. Certainly, if we look back at the impacts of the West African Ebola virus disease epidemic, what we can appreciate is that the Ebola epidemic not only had a major public health effect directly, but also indirectly on the ability for people to get access to care, much as we've seen with COVID-19, and certainly here in Canada has been highlighted over and over again. Just the complete stress on the healthcare system. We have to appreciate, though, in that many areas of the world that are hotspots for different emerging zoonotic viruses, public hospitals often lack even basic necessities, including constant electrical supplies, clean running water, or regular oxygen supplies. And as if all this wasn't bad enough, that's kind of the aspect of trying to figure out how to deal with the outbreak. We have to appreciate that we're learning more and more about these infectious diseases as time moves forward. Certainly, with the patient that I highlighted on the prior slide, when that patient was released from the hospital, we were able to collect semen samples from that patient on a monthly basis to look for any signs of potential persistence. There had been prior historical reports of potential sexual transmission and persistence in patients. And we wanted to look within our patient whether or not, or within this patient, whether or not we saw signs of persistence. And what we can appreciate is that the day before that patient left, retrospectively, we were able to show that patient had very, very high amounts of virus, not only from the amount of genome present in their semen, but also in terms of infectious virus as compared to their peak viral load right before they went into critical illness. And this has now been seen through a multitude of cases for males that have survived Ebola virus disease. And in fact, we've seen that persistence can occur anywhere from months now to years. And the most recent resurgence in Guinea in 2021 was linked back to a likely case of persistence. So we need to be able to find better mechanisms to provide diagnostic support for those patients. But what we also need to be able to do is appreciate long-term sequelae in patients as well. work that we've been doing with about 1,000 Ebola virus disease survivors and non-infected household contacts in Sierra Leone has demonstrated that many of the kind of early physiological impacts that we see in Ebola virus disease survivors that have been published previously, those carry on for many, many years post-recovery. And that includes things like eye pain, ear pain, neurological impacts, as well as arthralgia and other related disorders. And this was just focused on Sierra Leone. So realistically, there's a question now, how often are we seeing this? And do we need to start to push for better long-term care for patients post-recovery, not only during the time of outbreak? I'm going to switch gears to monkeypox virus and kind of talk about an ongoing public health emergency that we continue to be in. I cut my eye teeth on monkeypox virus. It was the first high containment virus that I worked on. Monkeypox virus has been around for a long time. First identified in 1958 in animals, not identified in humans till 1970. But once we, and this of course was during the kind of final stages of the global eradication campaign for smallpox. So as basically we started to see as we saw smallpox getting closer to being eradicated, monkeypox certainly gained more of a foothold in across endemic regions of Africa. And of course, we've since seen a global emergence in 2022. And what I want people to appreciate on the slide is that monkeypox virus is not new, right? If we look at Democratic Republic of Congo in this beautiful paper from Dr. Bohuma Tatangi and colleagues, what we can see is that cases have continually increased during the past 5 decades in Central Africa. West Africa, a little bit of a different story, but we have to appreciate our surveillance probably was not as strong as it was in DRC, a little bit mild over disease, and certainly other reasonings for why. So we have to appreciate that monkeypox virus is not new, and it certainly is not going away. Now, we also have to appreciate that our kind of perspective on monkeypox virus has had to change too. We traditionally have seen that transmission occurred through close contact. Most cases were driven by zoonotic transmission, so contact with wild animals, and then some limited secondary human-to-human transmission, but those often tended to end within about 6 to 7 generations of human-to-human transmission. And of course, we saw diverse case fatality rates depending on what region of Africa this was occurring in, whether Central Africa or West Africa. 2022 shifted things, though, where we saw basically the emergence of a new subclade of monkeypox virus globally. So the virus, as opposed to what we saw traditionally in endemic settings, where the virus was moving over from zoonotic sources into humans with some ongoing human transmission that was fairly limited, what we saw in 2022 was quite sustained human-to-human transmission with no zoonotic link, and as well a shift in the clinical presentation of what that disease looked like. So we're really left with trying to understand what happened with monkeypox virus. Has it been a change or a shift in viral characteristics, or has it been a change in the niche that it's been able to find within people? And of course, we have to appreciate that we saw primarily in 2022 the vast majority of cases were in those that are male, but those that also identify as men who have sex with men. How that parses out in terms of risk factors and transmission, I don't think we fully understand. But there is an aspect that we need to appreciate, that we've kind of been dealt a new card in monkeypox virus, and now we need to understand what happened in 2022 and whether or not we've been missing things in endemic regions. And of course, appreciating that while global cases have dropped off pretty precipitously over the past 6 months, we still see a high burden of disease within African regions, primarily within the Democratic Republic of the Congo. And the work that we're undertaking for this is really to try and understand the two facets of this particular disease of Mpox, both looking at Mpox in endemic settings, so trying to understand what circulation and transmission and risk factors look like in Central Africa as well as in West Africa, with added surveillance in East Africa, where we've not previously seen monkeypox virus infections, but then also bridging in what occurred in non-endemic regions. In Canada, we had about 1,500 cases. We had the ability to look back retrospectively to try to understand, what were risk factors that were related to monkeypox virus infections, what types of factors were related to transmission events or severity of disease, as well as looking at duration of immunity, whether that was gained through infection or vaccination. But I really want to highlight that, the work that we're doing here in Central and West Africa, these are regions that have ongoing burdens of monkeypox virus infections. We still are really at an infancy stage in trying to get vaccine distributed, as well as point of care diagnostics and therapeutics across these regions. So I'm very, very appreciative of the global response that we've had to monkeypox virus the last 12 months or so. But I would argue that, in the past 5 decades, we've largely ignored what's been happening here. And I certainly get fearful that we may continue to ignore that because the global burden has decreased. And of course, we have to appreciate again that with monkeypox virus, listen, this is a zoonotic virus. So until we understand where the virus is circulating in nature, we are going to continue to see different emergence events and certainly unpredictable emergence events. And part of this is trying to understand what are the primary reservoir hosts or intermediate hosts for animals that are linked back to monkeypox virus circulation. Certainly beautiful work done by UCLA, Annie Ramon and others have done some really pivotal work in looking at geographic distribution of animal species and of monkeypox virus infections across sub-Saharan Africa. And what we can appreciate is that the virus is likely not limited just to the regions where we've identified it. Certainly, if we look at different species that have been linked back to monkeypox virus carriage, that those regions extend well beyond the eastern borders and the northern borders of the Democratic Republic of Congo. So we need to increase our surveillance capacity in those regions. And really, just to kind of finalize or finish up here the talk. Our ongoing research, continues based on funding and interest from certainly from our grant funders and our colleagues. But for Ebola viruses, listen, we need to understand the molecular mechanisms that underlie persistence. Why does persistence occur? Where does it occur within the reproductive tract? And what does sexual transmission look like? And how do we defend against that or identify those cases of persistence? We also need to get additional surveillance data from our Ebola virus disease survivors to help inform basically long-term care for patients that continue to struggle with their recovery. And of course, integrate additional regions to look for region-specific variability in certainly some of these insights that we gain. For monkeypox virus, I think I've laid out much of that. We've got to increase our preparedness from a global standpoint, but primarily within sub-Saharan Africa, we've got to increase our accessibility for rapid testing for therapeutics and vaccination. There's no reason that after 2022, we shouldn't all have at top of mind the incredible burden that this virus has in endemic areas and the need for us from a global standpoint to try and truly get this virus contained. So with that, I'll just thank all of my, certainly all of my colleagues from all the various research initiatives that we're involved in. These are always surround yourself with smarter people than yourself is kind of my rule. And I've done that for years. And as well, want to highlight all the incredible funding that we've gotten from partners. Certainly none of this work would occur without them. And with that, I'll stop and thank you all very much.
Thank you so much for that wonderful presentation, Dr. Kinderchek. And now let me introduce our next speaker. Florian Kramer is a professor of vaccinology in the Department of Microbiology at the Icahn School of Medicine at Mount Sinai. He is also the principal investigator of the Sinai Emory Multi-Institutional Collaborative Influenza Vaccine Innovation Center and co-director of the Mount Sinai Center for Vaccine Research and Pandemic Preparedness. Kramer received advanced training in biotechnology and applied virology at the University of Natural Resources and Life Sciences in Vienna, and completed postdoctoral work in the lab of Peter Palisi in the Department of Microbiology at the Icahn School of Medicine at Mount Sinai. His research team focuses on understanding broadly reactive immune responses against the surface glycoproteins of RNA viruses, such as influenza, with the goal to develop better vaccines and novel therapeutics. As the principal investigator of the Sinai Emory Multi-Institutional Collaborative Influenza Vaccine Innovation Center, Kramer aims to develop improved seasonal and universal influenza virus vaccines, which induce long-lasting protection against drifted seasonal, zoonotic, and future pandemic influenza viruses. So we can just make sure that your slides are up and running, Dr. Kramer.
All right. Can you hear me?
I can hear you and I can see your screen. So the floor is yours.
Very good. Thank you very much. Thanks for the introduction. So what I'll try to do today is to look a little bit into what we know and what we do not know about viruses with pandemic potential, and what's needed for these viruses to actually develop their potential and to become a problem globally. We have already seen a very nice introduction by Professor Kindrachuk about outbreaks and that happen globally. Here's just a short list of outbreaks since 1994 that were in the media. And what you can see here in red are two outbreaks that actually led to pandemics. One is the H1N1 pandemic of 2009. The second one is the SARS-CoV-2 pandemic of 2020. Of course, there were many more outbreaks. There were many more outbreaks than actually listed here. These outbreaks happen constantly, but many of them stay small and are self-limited and don't even make it to the media. If you're interested in these maybe smaller outbreaks that happen all the time, you can sign up at ProMed Mail and you will get emails actually with updates of what's happening globally. And yeah, I hope you'll still be able to sleep at night after you signed up there. So a lot of these outbreaks are caused by viruses that are zoonotic in nature, meaning that they jump from animals into humans. I'm showing some of the culprits here. Waterfall, for example, but also chickens are responsible for amplifying avian influenza viruses that might jump into humans. The same is true for pigs, but pigs, for example, have also been implicated in transmission of Nipah virus to humans. Camels, for example, can transmit MERS coronavirus to humans. A lot of the sarbecoviruses that we are fighting with, SARS-CoV-1, also SARS-CoV-2, probably came originally from bats. Here we have another type of bat, a flying fox, which is usually the reservoir for Nipah and Hendra viruses. And then even animals that are very, very close to us, like in New York City, for example, rats, can spread viruses like hantaviruses to humans. So typically these viruses jump from their animal reservoir into humans. And as we also have heard already, the number of outbreaks is increasing, and that has several reasons. First of all, of course, we're much better at finding infections and diagnosing them correctly and finding the pathogen. If you go back 50 years, that wasn't so easy, but now we have the technology to do it. And that's certainly one factor why more of these infections are detected. Another thing is that the world is better connected, right? Somebody might get infected somewhere in a rural area, let's say in sub-Saharan Africa, but that person might actually travel to New York City and then go to a hospital there and might be diagnosed or spread the virus locally to people in the city, right? So there's this connection, and this is shown here by this map that shows airline routes. That is really something that can be problematic and also increases how often we detect these viruses. One additional and important point is there are more people, and if there's more people, there's more chances to catch a virus from an animal. And that's not the only factor here. If you have more people, you have more domestic animals because you need more food production. That increases the interface between animals and humans. And the larger that interface is, the higher the chances that the virus jumps. We've already heard about climate change. Climate change is a big factor as well. One point in terms of climate change is that vectors, meaning mosquitoes, ticks, and so on and so forth, spread globally, right? We have seen, for example, now Aedes albopictus in Europe, and that is a mosquito that is capable of spreading a lot of mosquito-borne viruses. But climate change might also lead to behavioral changes of humans, but also animals that might increase transmission of viruses to humans. And then in addition to that, we have a lot of natural habitat destruction, right? And this can trigger ecological changes, but it also changes human behavior and human range, right? We go into habitats where we typically don't go, and that means we're exposed to viruses that are around there. So my expertise is influenza virus, and since early 2020, unfortunately, also SARS coronavirus too, but originally I'm an influenza virologist. And so I'll explain a few of these concepts that I'll go through by looking at flu. And so I wanted to give a short intro about influenza viruses. They are part of the Orthomyxoviridae family. For bona fide influenza viruses, we have influenza A, B, C, and D. A and B are really clinically relevant for humans. C causes common colds. And D has been found in cloven-hoofed animals like cows and sheep, for example. But it seems it might also be able to transmit to humans in some cases. And so these viruses have a lipid envelope, which is shown here in yellow. They have a -10 single-stranded RNA genome, which is segmented. And that's one of the big issues with the virus. The genome is shown here on the inside. And you can see the 8 genomic segments. And the different segments encode for a number of different proteins. One segment encodes for the hemagglutinin, which is the major surface glycoprotein. And for influenza A, there's a huge diversity of subtypes of hemagglutinin. Actually, there's 18 of them. Another segment codes for the neuraminidase, which is the second surface glycoprotein. So compared to SARS-CoV-2, we have 2 glycoproteins here. And that also comes in 11 different subtypes for influenza A viruses. And the other segments then code for the matrix protein, an M2 ion channel, the polymerase and the nucleoprotein, and then NS1 and the nuclear export protein. So when we look at influenza virus and the infections it causes, we see that we have an extremely wide host range. It causes a spectrum of mild to severe respiratory disease in humans. And we have 2 forms. We have epidemics. This is seasonal influenza, and this is caused by influenza A and B. And we have pandemics. And pandemics are so far exclusively caused by influenza A. In terms of burden, when we look at epidemic or seasonal influenza, we have about 3 to 5 million severe cases every year and between 300,000 and 650,000 deaths. These numbers are from before the pandemic. During the pandemic, there was little circulation, but now the virus is unfortunately back. And so in the US, the virus kills between 3 and 49,000 people every year. And then the other form is pandemic influenza. And the strongest example here is the 1918 H1N1 pandemic that claimed approximately 40 million lives. And I always like to show this figure here, which is the life expectancy in the United States between 1900 and 2001. And you see this big tip here. And this is the cost of the pandemic. So this is the impact of all these young people that died because of H1N1 infection. Of course, influenza virus can also infect animals, and it causes similar disease in mammals as it does in humans. And it can infect ferrets, pigs, seals, horses, whales, cats, dogs, basically almost every type of animal. And then when we look at avian species, which are the real hosts of influenza, there it mainly infects the GI tract. Mostly these infections are asymptomatic, but sometimes you have symptomatic infections, specifically when we talk about highly pathogenic avian influenza virus, and we'll get to that. So what I'm showing you here are the dynamics of influenza virus subtypes in humans in the last approximately 100 years. So we had our H1N1 pandemic in 1918, and then the virus established itself as seasonal virus in the population. And in order to do that, because of course people get neutralizing antibodies, the virus has to change slowly over time, and that's what we call antigenic drift. That's why these arrows change here. In 1957, we had another pandemic, and that was caused by H2N2. And interestingly, this virus kicked H1N1 out. So there's an interesting interaction of these viruses in the pandemic, in the population, and they compete with each other. So H2N2 then circulated until 68 and drifted a little bit too. And in 68, we had another pandemic with an H3N2 virus. And that virus is still circulating as seasonal virus. In 1977, H1N1 came back, circulated until 2009. And then we had the H1N1 swine flu that jumped into the population and took over from H1N1 here. And so currently we have H1, H3, and influenza B circulating in humans. The problem is that we don't really know what the next jump will be, what the next transmission from animals into humans will be, what the next pandemic will be. Looking at that, the only thing we know is there will be another one. So again, where do these viruses come from? I already mentioned that there's a lot of these subtypes, and this is shown here. On the left side, you have a phylogenetic tree of hemagglutinin subtypes. On the right side of neuraminidase subtypes. And you can see for influenza A, we have two groups, group 1 hemagglutinins, group 2 hemagglutinins, and then, of course, influenza B a little bit further away. And these red stars here indicate viruses that have been circulating or are currently circulating in humans, H1, H2, H3. And in blue stars, we have viruses that have been implicated in zoonotic infections like H5 and H7, and often with a deadly outcome. And the same is true for the neuraminases. There's always pairs, of course, like H1N1, for example. Going back to the animal reservoir, the central reservoir are aquatic birds, but the viruses spill over into marine mammals, into domesticated animals, into humans, into other birds, and also into bats. I think we can remove that question mark here. This has been now shown quite extensively. And these spillover events into humans happen actually quite often. Here I just have a list. You can see all these purple events are basically spillovers from animals into humans, often without a lot of consequences. Of course, they might end deadly for the person who got infected, but then often there is no further on spread of the virus in the human population. And I've also included spillovers of avian influenza viruses into mammals like H3 and 8 here, or H10 and 7. And this goes until around 2017, and then here are more recent spillovers that we have seen. And here's also the benzootic H5N1 virus. We'll talk a little bit more about that, but that's currently a big problem. And then there's the ever-looming threat of H2N2, which was kicked out of the population, but is still there in birds. And we know that virus can certainly cause a pandemic. And so I wanted to go through important factors that are needed for these viruses to cause large outbreaks or to cause pandemics. And again, I'll go into examples for influenza. That's why I showed the intro about influenza. But these are basically general principles. And the first important factor is that there is an animal-human interface. There needs to be contact, right? If there's no contact, the virus cannot jump from animals to humans. And so there are a few ways how that could happen. There's a few things that need to be pointed out. The first way is basically directly from wild animals to humans, and that happens. This can happen by direct interaction with animals or urine or feces of these animals. Hantavirus infections, for example, happen like that. Another factor is bushmeat, right? So if people harvest animals, and if you think bushmeat, don't just think African countries. Think people who hunt ducks in the US, for example. People who hunt deer, right? All of this I would classify as bushmeat in a way. So that can happen. People can get infected when they hunt animals, when they process the animals that they hunted. And then via vectors indirectly, right? For example, if you have non-human primates who are infected with yellow fever, then that can be transmitted via mosquito to a human. An important point here are also wet markets, where sometimes wild animals are sold, but even if it's domestic animals like chickens, that can be problematic. And we'll talk a little bit about that. So changing policy on wet markets is something that would be highly desirable from a pandemic preparedness point of view. Another scenario that we often have is that we have transfer of viruses from wild animals to farmed animals and then on to humans. And so the farmed animals serve as amplifier because you have a lot of them, right? In often closed spaces. And so the viruses really have it easy to amplify there and to grow and grow and grow, and there's more and more virus. And so these large-scale outbreaks in farmed animals can often lead also to viral mutations that increase risk for humans, and I'll show you an example. And then it's also important to think about where transmission happens. Rural areas with low population density have a lower likelihood to support virus spread. That means even if a zoonotic infection happens, that person then has fewer interactions with other people, and the population density is lower, so maybe the virus doesn't have as many chances to jump from one human to another, while transmission events in cities are much more problematic because you have a much higher density and many more interactions. So a few examples of problematic examples, and I'm actually trying to stick to North America here. One problem is, as I said, wet markets, right? You bring animals from different farms to a market. The animals are still alive. They are often held there overnight. They can basically exchange viruses. Viruses can amplify directly at the market. And then there's interaction with customers, right? Believe it or not, we do have wet markets in New York City. And believe it or not, H2N2 virus, which is the virus that caused a pandemic already in 1957, is on a frequent basis detected in chickens in these wet markets in New York City. This is actually shown here on the right side, all these red dots here. In the different colors, not the wild bird ones, but the other ones are H2N2 isolations from wet markets in the northeast of the US, and that includes New York in green here. So this is something that has a high risk because these viruses we know have caused the pandemic, and we have them in our cities, and currently we don't do much about that. So that's something to keep in mind when we talk about risk. Another important point, and again, an example from North America, is that again, when viruses from wild birds jump into domesticated birds that are held in large congregations in a farm setting, the virus can amplify and it can mutate, and that can make it more dangerous. And we have two examples of that, one from Indiana from 2016 and one from Tennessee from 2017. One was with an H7N8 virus and one with an H7N9 virus. So those were low pathogenic viruses circulating in avian species, and then they were transmitted into a chicken farm or into a poultry operation. And the virus started to amplify, and it changed. And then, of course, when it changes, it can become more dangerous for humans. And also there's a lot of virus that the workers at these farms are exposed to, right? The interesting thing here is the change that happened, and this is well documented in both outbreaks. Influenza viruses, they have a hemagglutinin, and to activate that, like the spike protein of SARS-CoV-2, needs to be cleaved by a protease. And typically this cleavage site is monobasic. When it becomes polybasic, then a low pathogenic influenza virus becomes a high pathogenic influenza virus. And this often happens when you have this massive amplification of virus in chickens, for example. And this is exactly what happened on in those two farms. The virus that went into the farm was low pathogenic, started to mutate. there are insertions that happen into the hemagglutinin gene, and then you have the creation of a polybasic cleavage site. And this was recorded on site there, and then this virus is now highly pathogenic. And so the point here is that these changes unfortunately occur naturally in farm settings, and they can create potentially dangerous viruses for humans. The last example here in terms of interaction is the transmission of H3 and 2 variant swine viruses from swine into humans at country fairs. And so people have pigs that they show at country fairs. People interact with them. On the left side, you see a picture of that might happen. And so these viruses, which are actually swine viruses, these are not human seasonal H3 and 2s, have been jumping into people who attend these country fairs on a regular basis. There was a huge increase in these cases in 2011, but basically almost every year we detect these cases. And of course, this could lead to onward transmission and to a new pandemic right in our backyards. Okay, the next important factor is the virus now jumped into a human, but is it able to spread from human to human? And that's a really important factor, right? And typically, from an epidemiological perspective, we describe that with R0, or the basic reproduction number. And so that means an R0 of 1 means that one infected person infects one person. An R0 of 3 means one infected person infects 3 additional people. If the R0 is below 1, the virus will eventually die out, of course. And so this is different for different viruses. Measles has a very high R0, between 11 and 18, while seasonal flu, for example, has a much lower one, around 1.3, maybe 1.5, still spreading in the population, right? But it's much easier to stop in a way. And we saw that with all the masking and the social distancing during the pandemic. Seasonal influenza was basically not, I wouldn't say eradicated, but the transmission was very, very limited. How high this R0 is also has to do with the way these viruses are transmitted, right? The viruses we are most worried about are viruses that are transmitted via respiratory droplets or aerosols. And that's because they're really hard to, this is really hard to stop, right? You need masks, you need control of air quality and so on and so forth to really stop these viruses, while other transmission modes are much easier to control. And for transmission via the respiratory tract, we often, the virus often requires efficient replication in the upper respiratory tract. And so that's kind of a hallmark of a virus that has a lot of pandemic potential. Of course, you have other ways of transmission as well, via fomites, meaning contaminated objects, direct contact, bodily fluids. With Ebola, for example, the transmission can occur via vector, sexual transmission, via the blood supply, or just zoonotic transmission. But these things are much easier to control than viral spread via respiratory droplets or aerosols. And another important factor here are super spreaders, right? Sometimes you have these explosive outbreaks which are only triggered by one person. And instead of infecting 1 or 2 or 3 people, these people can infect hundreds of people. And we don't understand the mechanism behind that very well. Just straying a little bit from influenza, I wanted to show you one example of a virus that has the ability to spread via the respiratory tract in humans, has a very high case fatality rate, but has an R0 that's currently too low for sustained spread. And that's Nipah virus. Nipah virus is a paramyxovirus with a case fatality rate typically above 50%, often approaching 100%. And this infection occurs in Bangladesh, Malaysia, and India. In Malaysia, typically the virus is transmitted from flying foxes to pigs. They amplify it, and then you get transmission to humans. While in Bangladesh, often people are infected when they harvest palm sap. The bats like that sap, the people like it, and when you put containers on palms to basically collect that, the bats drink from that and then contaminate it, and then you get basically infection of humans, and humans can transmit it to other humans via the respiratory route. The good thing is this virus has an R0 of below 1. So again, it doesn't really spread between humans efficiently, but it probably can mutate and can increase that R0. And so this is really a virus to watch out for, specifically with that case fatality rate. That might be one of the candidates for another pandemic. For influenza, we know actually a lot what the factors, the molecular factors are that are needed for human-to-human spread. The first one is really the receptor specificity of the virus, right? Influenza with its hemagglutinin binds to sialic acid on cells to infect them. Now, the sialic acid on these cells can be linked in different ways, either with an alpha-2-6 or an alpha-2-3 linkage. And typically, humans in their upper respiratory tract have more of an alpha-2-6 linkage. And in the lower respiratory tract, there's also alpha-2-3 linkage. But in chickens, both is present, right? And so basically, a virus from chicken often is specific for alpha-2-3 linked sialic acid. And when high amounts of this chicken virus are inhaled by a human, the virus might be able to replicate in the lung, but it's not doing very well in the upper respiratory tract, meaning that there's likely no transmission. Of course, there's other factors that come into play here too, including pH stability and cleavability of HA, but this receptor specificity is important. In addition to that, these viruses also need to be able to interact with our cellular factors. And one important factor is interactions with the Pol2 polymerase. And so the influenza virus polymerase PB2 needs to have a specific configuration in order to be able to do that. And so often we see that avian influenza viruses have an E in position 627, but if that mutates to a K, we get very good interaction and then much more replication of these viruses, and that enhances their potential too. And in addition to that, humans have restriction factors that restrict growth of avian influenza viruses. One of them is the MX protein, but influenza viruses can mutate to overcome this restriction, and that's a factor here too. Typically, when an influenza pandemic happens, it's not caused by a virus that transmits directly from birds into humans and then adapts to humans. It's usually a mix. Very often, it's a reassortment between a human or a mammalian influenza virus and then an avian influenza virus. What do I mean with reassortance? So I told you that these viruses have genomic segments, and they can exchange them when they infect the same cell. And the outcome of this infection could be a virus that has new hemagglutinins and neuraminidase, to which humans are immunologically naive. But this new virus might have a replication machinery from a mammalian adapted virus and thus replicate very well in humans. And the genesis of these reassortance can be very complicated in some cases. For example, for the 2009 H1N1 pandemic strain, we know that at some point in time, a mixture was generated between a classical swine virus, a North American avian virus, and a human H3N2 virus in swine. Not at the same time. This was probably happening sequentially. Then this reassortant was circulating in pigs, and then that pig virus reassorted with another pig virus, and that resulting virus then jumped into humans and caused the 2009 pandemic. So it can get very complicated. However, there are also limited reports where avian influenza viruses jump into mammals directly and start to mutate enough in order to spread efficiently between mammals. And one report, and most people might not be familiar with that, is actually the outbreak, an outbreak with H10N7 virus in 2014 in harbor seals in Denmark and Germany. So what happened here was that at some point in time, an avian H10N7 virus jumped into harbor seals and started to mutate there, and actually killed a large proportion of the harbor seal population in Europe. But by mutating, it acquired mutations that allowed it to to transmit among mammals, not just seals, but ferrets, for example, as well. And so people got isolates of these viruses, the avian virus, the early seal virus, and the late seal virus. And when you then do transmission experiments in the laboratory with ferrets, you see that initially the avian virus wasn't transmitting from ferrets to ferrets well, but the virus that caused this late outbreak in seals was actually able to transmit very efficiently, and this could be tied to mutations in the hemagglutinin. Another important example, another important story is H5N1, right? Recently, highly pathogenic H5N1, the clade 2.3.4.4b, made it from Europe to the United States. There was a lot of media attention to that. There were a lot of outbreaks in poultry operations, and so this virus showed up here in the US in the end of 2021, beginning of 2022, and has since then spread all over the US, Canada, Mexico, down to Central America, and is now really down in South America. So it might actually even spread to Antarctica. And what we have seen is that a lot of birds are affected, but the virus also transmits to mammals, specifically mammals that feed on bird carcasses, and can cause severe disease and death in these animals. But typically, there is not a lot of mammal-to-mammal spread with this virus because it's still an avian influenza virus. But again, there was a recent report that raised concerns, and that involved, again, farmed animals. This was from Spain with the same H5N1 virus, where it seems that the avian version, a highly pathogenic avian H5N1 virus, somehow made its way into a mink farm and then started to get transmitted from mink to mink. And they realized that because the mink started dying, right? And so when that happens, the virus can mutate again and acquire mammalian adaptive mutations. And that virus then is, of course, dangerous for humans and might actually give rise to another pandemic. So that's, again, something to watch out for. And we really have to make sure that our farms are secure. I think that's one of the take-home messages here. The last factor that I wanted to talk about is immunity. And that's also important. When you look at an emerging virus or virus of concern, you want to know how much baseline immunity against that virus is there in the population and in different segments of the population. And this became very relevant in 2009 with the H1N1 pandemic. A very early observation that was made was that older people are actually not really getting infected a lot by this virus. And this is shown here. This is positive tests in different age groups, right? And so we have a seasonal H3 and seasonal H1 here. And as you can see, there was little H1 during this study period, but it's kind of, happening. The H1 infects younger people as well as older people. And the same is true for seasonal H3 and 2, right? But when we look at this new 2009 H1N1 pandemic virus, we see that mostly younger people are infected, and people above 50 have a much lower infection rate. The reason for that was that these people had neutralizing antibody against this new virus. And that came basically from exposure to old H1N1s related to the 1918 pandemic virus, right? And so you can see that here, this is now antibody neutralizing activity in different birth cohorts, right? So we're starting here on the left with very old people, and here on the right, very young people. And you can see that people up to, at that point, the age of approximately 50, had good numbers of neutralizing antibodies, but then this declined. And that is actually the explanation why older people didn't get infected so often and didn't have severe infections with the 2009 H1N1 pandemic virus, while it did a lot of damage in younger people. And so the reason was that the 1918 H1N1 virus and the 2009 H1N1 virus are actually antigenically related. The nice thing is this also goes the other way around. Now we have a lot of immunity against H1N1 because this 2009 virus circulated and is still circulating in humans. And this immunity probably protects us against the 1918-like H1N1 virus. So this 1918 H1N1 virus, which people have in biosafety level 3+ laboratories, and which was considered very, very dangerous, would probably now be a harmless virus for the population because we all have immunity against it. And so this is my last slide. What do we need to know? I think we need to know what's out there. And I showed you a lot of influenza examples because we have good surveillance systems for influenza, but we don't have them for a lot of other viruses. There are a lot of question marks, right? What we really need is a global surveillance system for all virus families that include viruses of concern. And we need to do the surveillance in animals and in humans. And we specifically need to do the surveillance at the interface between animals and humans. And that doesn't just include farms and markets, that also includes surveillance in urban areas. So we really need to know what's circulating. But that's not enough, right? We also need to know if we get the sequence of a new virus that's circulating somewhere, we need to know what to look for in order to say, okay, this is a virus that's dangerous, or this is a virus that is not dangerous. And that requires that we do phenotyping experiments. We figure out which genetic markers are actually associated with problematic phenotypes, right? And that helps us to better predict the danger that can come from a virus just by looking at the sequence. And in addition to that, I think we need to understand factors that drive virus emergence. And this is something where a lot of science needs to come together. We need to look at the ecological side. We need to look at climate factors. We need to look also even at the economic side, right? Changes in production systems, for example. On the sociological side, changes in human behavior. So we need really an interdisciplinary approach that looks at what factors drive virus emergence. I'm not going to go into vaccines and therapeutics. That would be another talk in itself. I think we need much more preparedness there. But I think in order to protect ourselves, we need to understand what's out there. If you run through the world blind, you will probably run into a tree or a wall at some point in time. But if you can see, you can avoid these things and you can prepare for them. And with that, I'll finish, and I'm looking forward to the discussion later.
Thank you so much, Dr. Kramer. As a reminder to the audience, you can submit your questions at any point during the webinar, and we will get to as many as possible after our final speaker. Additionally, for more information on pandemics after the symposium, please check out some of our recent articles. You can find more information on those by navigating to the handouts tab on the right side of the screen. And so now I'll introduce our next speaker, Dr. Tan. Chiwa Tan is a senior research fellow in Lim-Fa Wang's laboratory at Duke NUS Medical School. He completed his PhD training in medical microbiology and virology at the University of Malaya, and his research focuses on bat-borne viruses, including bat filoviruses, coronaviruses, and orthoreoviruses. During the COVID-19 pandemic, Tan led the invention of the SARS-CoV-2 surrogate neutralization test, which was the first serology test for SARS-CoV-2 antibodies that was granted US FDA emergency use authorization approval. Since then, he has established a surrogate virus neutralization test, which can detect antibodies against SARS-CoV-2 variants of concern and other SARS-related coronaviruses. Tan has also made key discoveries connecting SARS pre-exposure and mRNA-based vaccination to pan-Sarbecovirus immunity. So we'll make sure your slides are up and running, Dr. Tan. And the floor is all yours. Take it away. You might be muted, Dr. Tan. I can't hear you currently. You might want to try logging out and back on, Dr. Tan.
Hello.
Hi, Dr. Tan. I can hear you now.
Okay, sorry about that. So due
No.
to some technical problem.
Yeah, no problem.
Thanks for the introductions. So in today's talk, I'm going to talk about like the SARS-CoV-2 surrogate virus neutralization test that we have invented and the discovery that we have made for the next generation coronavirus vaccines. So since I came from a bat lab we study the bat immunology and bat viruses. So I would like to give some introductions about why bats are special. So bats are known reservoirs for numbers of highly pathogenic viruses, including Nipah virus, Ebola, SARS, and MERS, and also the recent SARS-CoV-2. So bats actually is unique in the sense that it have a balance between the immune tolerance and enhanced host defenses responses. So if you look at the this slide over here, so in what indicated here is like bats actually have a high expressions of the antiviral defenses such as interferon or either IgG or the heat shock proteins. But at the same time, it have actually a dampen of some of the information pathway as well as the STING pathway. So this actually make bat a very unique reservoir to carry viruses. So over the last 2 decades, we evidenced that there are 3 coronavirus outbreaks that cause epidemics and pandemics. So this includes the SARS outbreaks in 2003, MERS outbreak since the 2012, and the current COVID-19 pandemics. And what very important here is all these coronaviruses are actually originate from bats. So in fact, if you look at the 7 human coronavirus that known to infect humans, 5 are actually originated from bats. So this highlights the fact that the bats actually carry coronaviruses with a spillover potential. So this heat map is very important to show you that the relatively risk distributions of the emerging zoonotic disease events. And as highlighted over here, as you can see in the with a red circle, Asia is actually a hotspot of emerging zoonotic viruses. So if you look at the map over here, we focus on the SARS-related coronavirus in Asia. So as you can see that there are multiple SARS-CoV-1 or SARS-CoV-2 related coronaviruses has been detected in animals, especially in Rhinoceros bat species. And this also highlights there is a very rich diversity of the SARS-related coronaviruses in Asia. So it could be a potential threat to the human populations. So in one of the studies that I have involved, we identified SARS-CoV-2 related coronaviruses, the RSCCS 203. So in Rhinoceros bat in in Thailand in June in Thailand. So apart from this, we also provide a very important evidence of past exposure to SARS-CoV-2 related coronaviruses in 4 out of 100 bats in the study site, and 1 out of 10 pangolins that confiscated in Thailand in June 2020. So there are 2 possibilities for the positivity in one of the pangolin. So the first, it could be the spillback from the SARS-CoV-2 infected pangolin handler, or the second possibility is the pangolin were actually previously infected by a SARS-CoV-2 related coronaviruses in the wild. So in this study published in Nature Com, highlight that the spillover of the SARS-related coronaviruses in South Asia is actually more often than what we previously thought. So this study actually estimated a median of about 66,000 people are infected with the SARS-CoV-2 related coronaviruses annually in the Southeast Asia regions. So we need a better vaccines that able to prevent us from the current or the future coronavirus infections. So the aim of today's talk is like, we'll give you introductions about the surrogate viral neutralization test that we invented, and how we use this platform to discover on the discovery of the pan-cervical vaccination strategies, and also how this platform is evolved to allow surveillance of the pathogens with a pandemic potential. So this is a very nice Swiss cheese model of immunity. So our immune system comprises of different layers of barriers, and each of these barriers are not a perfect barriers. So there are holes here and there. So we need a combination of these barriers to prevent us from a severe disease. And one of the major components of this barrier is a neutralizing antibody, which is our lab focus. So you may question like why we study neutralizing antibodies. And if you look at the curve over here, then this study was actually done by a Mount Davenport group from Australia in 2021. So what they did is that they used the vaccine efficacy data from the clinical trials, and they used that, and then they determine the neutralizing titers from each of these type of vaccines. So if you look at this curve, the vaccines candidate, for example, the mRNA vaccines like the Moderna mRNA vaccines or the Pfizer mRNA vaccines, which able to induce high level of neutralizing antibody, are usually associated with high level of protective efficacies. So this actually highlight that the neutralizing antibody level are good predictive of the immune protections from the symptomatic SARS-CoV-2 infections. And the gold standard way of determining the neutralizing antibody is actually through the blood reduction neutralization test or the live viral neutralization test. Blood reduction neutralization test is one of the example. So as shown over here in this diagram. So if the serum sample carry neutralizing antibody, it will actually neutralize the virus and prevent the virus from infecting the cell and therefore blocking the blood formations. But SARS-CoV-2 is a biosafety level 3 pathogens, and you have to perform this assay inside a biosafety level 3 lab. And this actually, which is more tedious, low throughput, and time consuming. Therefore, we need a surrogate system that actually allow us to have a feasible for rapid mass testing. At the early of the pandemic, we came up with an idea of using a SARS-CoV-2 spike and the receptor ACE2 as a surrogate assay to determine the neutralizing antibody that block ACE2 RBD interactions. So let's look at the convention viral neutralization test as shown over here. So this test requires live SARS-CoV-2 and a cell that expressing the human ACE2. So obviously, this have to perform in the biosafety level 3 lab. So in the presence of neutralizing antibody, the antibody will bind to the spike proteins and block the spike from entering the cell and prevent the infection cycle. So while in our ELISA-based surrogate VNT assay, we use a small portions of the spike proteins known as the receptor binding domain, or RBDs. So the domains is actually responsible to bind to the ACE2. So these RBD are conjugated with a HRP enzyme for detection purpose. So without the neutralizing antibody, the RBD will bind to the ACE2 receptor that coated on the ELISA plate. When substrate is added, the signal will develop. So when there is a presence of neutralizing antibodies, so the antibody will bind to the RBD and block the RBD ACE2 interactions. And the unbound RBD will be removed during the washing step. And when the substrate is added, we will see a no signal or reductions of the signal. So we have demonstrated that the SVNT platform actually have a very good correlation with the plaque reduction neutralization test, as shown in this correlation curve over here, with an R-square of 0.95. So this also highlights that the majority of the neutralizing antibodies induced during SARS-CoV-2 infections or vaccinations are mainly targeting on the receptor binding domains. So as the virus is continued evolve from ancestral Wuhan HU1 strain to the Omicron XBB now, so our ELISA-based SVNT platform might not be feasible to detect neutralizing antibody targeting different SARS-CoV-2 variants. So we have to come up with a robust platform that allows multiplexings. So, and therefore we establish a multiplex SVNT platform using a Luminex technology. So in this multiplex SVNT platform, we now coded the RBD of the different SARS-CoV-2 variants onto a different regions of the Luminex bits. And then we now use the PE label AC2 for detections. So this allow us to detect, by using this platform, is allow us to detect the neutralizing antibody targeting against SARS-CoV-2 variants or other animal SARS-related coronaviruses in the same reactions simultaneously. So and now our platform are now comprised more than 30 plex, and which allow us to have a high resolution characterizations of the neutralizing antibodies. So now I'm going to talk about the most exciting discovery that we have made. During the SARS outbreak in 2003, there are about 200 cases of SARS reported in Singapore. So early of the COVID-19 pandemic, we recruited these SARS survivors in our study, and we analyzed whether they have a cross-neutralizing activities of their serum so that we can use their plasma for convalescent plasma therapy. But unfortunately, there is no or limited cross-reactivity neutralizing antibody in these SARS survivors. As part of the follow-up, so we recruit these individuals back to our cohort study again after they had received their COVID-19 vaccinations. And to our surprise, the data generated using our multiplex SVNT, we clearly observed that SARS survivors who received 2 doses of the mRNA vaccines are able to induce high level of cross-reactivity neutralizing antibodies that neutralize SARS-CoV-2, SARS-CoV-1, and all the other animal SARS-related coronaviruses that are tested in our platform. So despite the individual who have infected with the COVID-19 followed by mRNA vaccinations, the most they can produce is the neutralizing antibody that targeting the SARS-CoV-2 related coronaviruses, and there are limited cross-reactivity neutralizing antibody against SARS-CoV-1 coronaviruses. So in another study that we worked together with Malik group from Hong Kong University. So we studied different priming combinations and the cross-reactivity neutralizing antibodies. So if you look at this curve, so the y-axis is the RBD cross-reactivity and the x-axis is the average percentage of inhibitions. And clearly you can see one very obvious outlier over here, which is the SARS survivor who received 2 doses of the Pfizer mRNA vaccines. And if you look at the reactivity, is actually outperform all the other combinations, including the SARS survivor who received the inactivated vaccines. So this actually suggests that the mRNA priming are very important to induce the high level of cross-reactivity neutralizing antibodies against all these SARS-related coronaviruses. So now if you look at the B cell characterizations, so we collect the B cell from this SARS survivor as well as other like the healthy vaccinated or the SARS-CoV-2 infected individual followed by the vaccinations. And the B cell collected from the COVID-19 vaccinated SARS survivor is the only group that actually can be double stamped by the RBD from the SARS-CoV-1 and SARS-CoV-2. So this actually indicates that the antibody that display on the B cells that can bind to the highly conserved epitopes that are shared between the SARS-CoV-1 and SARS-CoV-2. So we get a very good, excellent data in humans to show that the prior exposure to the SARS infections followed by a SARS-CoV-2 vaccination are able to induce high level of cross-reactive neutralizing antibody. So now we came up with a pan-sarbegovirus cross-clade vaccination strategies. So if you look at the family tree over here, SARS-CoV-1 and SARS-CoV-2 are indeed form 2 separate clades over here. So individuals who have pre-existing SARS-CoV-2 immunity carry neutralizing antibody targeting the immunodominant epitopes, and maybe there are some small amount of cross-reactivity neutralizing antibodies against the highly conserved epitopes. But when this individual receive a SARS-CoV-1 spike immunizations, they will actually generate high level of neutralizing antibody targeting the common epitope, common highly immunodominant epitopes, but also it will actually force the B cell to produce more neutralizing antibodies that are targeting on the highly conserved but are less immunogenic epitopes. So apart from the vaccine development, so we also able to collect the B cell from this SARS survivor who received the mRNA vaccines, and we managed to isolate multiple pan-sarbego monoclonal antibodies that are actually remain potent against the current circulating Omicron variants. So what are the lessons that we have learned during the COVID-19 pandemics? Early detections and containment through the active surveillance or risk assessment of the zoonotic viruses in human-animal interface are very important. So we have to always do a surveillance of the pathogens with the high
Dr. Tan, I think we lost your audio again, unfortunately.
You hear me again? Sorry.
Oh, there you're back.
I don't know what's wrong with my. I'm sorry, I don't know what's wrong with my microphone now. All of a sudden, so
Nope.
So I will the lessons that we learned from the COVID-19 pandemic. So what I highlight is the early detections and the containments through the active surveillance or the risk assessment of the zoonotic virus in human-animal interface is very important. So secondly, we have to anticipate the future epidemic or pandemic and to preemptively establish vaccines or therapeutics against the all these viruses. And lastly, so the next generation vaccines that we should aim to develop must comprise of these three major components. It must be able to induce broad spectrum of immunities, and the vaccines are able to induce not only the systemic immunity but also on the mucosal immunity, and also the long-lasting. So this slide actually show the words that are published in 2012 in Lancet. So it's very important and highlight the needs of active surveillance and to forecast the outbreak and as well as the early detection of the threat, so that we have a rapid response to the outbreak so that we can actually stop the outbreak from becoming the pandemic. So many viruses has been discovered in animal reservoir, but if you think about it, there's a limited risk assessment have been done on these viruses. So this perspectives published in Science actually show a very good pipeline that we need to do. So we have to establish the experimental assessment pipeline to characterize the pathogenicity of these viruses to human, and if this is highly pathogenic to humans, whether our pre-existing immunity, population immunity are sufficient to stop these pathogens to become a pandemic. If not, what we should do, and should we update our vaccines, or should we develop other therapeutic to targeting these highly pathogenic viruses? So altogether, government, scientists, epidemiologists, policymakers, and the pharmaceutical industry partners should all work together on the pandemic preparedness. So as part of the active surveillance, so we have established a comprehensive multiplex S20 platform that are not only capable to detect the neutralizing antibody against the SARS-CoV-2 related coronaviruses, but now we have established a platform that allows us to detect other coronaviruses such as MERS coronaviruses, as well as the Hannibal viruses. So I would like to end my talk with this quote from Larry Brilliant. So outbreaks are inevitable, but pandemics are optional. So we can't stop an outbreak from occurring, but we should have the tools or a platform to stop the outbreak to becoming a pandemic. So are we prepared for the next pandemic, or can we make the COVID-19 the last pandemic? Thank you for your attention, and sorry for the loss of the microphone. Thank you.
Not a problem at all. Thank you so much, Dr. Tan, for your presentation and for persisting through those technical difficulties. We really appreciate it. And so now let me introduce our final speaker, Dr. Popescu. Saskia Popescu is a term assistant professor in the biodefense program within the Schar School of Policy and Government at George Mason University. Popescu is also an adjunct professor in the Mel and Edith Zuckerman College of Public Health, Epidemiology, and Biostatistics program at the University of Arizona, as well as an alumni fellow of the Emerging Leaders in Biosecurity Initiative at Johns Hopkins Bloomberg School of Public Health Center for Health Security. She received her PhD in biodefense from the Schar School in 2019, and also completed a master's in public health with a focus on infectious disease epidemiology, as well as a Master's of Arts in International Security Studies from the University of Arizona. Popescu currently serves as a member of the Federation of American Scientists Coronavirus Task Force and is a member of the Committee on Data Needs to monitor evolution of SARS-CoV-2 within the Health and Medicine Division of the National Academies of Sciences, Engineering, and Medicine. Prior to joining George Mason University, Popescu worked as an infection prevention epidemiologist in several large healthcare systems, working to enhance readiness and biopreparedness. Her research addresses gaps within global health security and biodefense, and how to integrate antimicrobial resistance into global health security initiatives. And I can see your slides perfectly, Dr. Popescu, so take it away. I think we might also be having some audio trouble here where we're not able to hear you, Dr. Popescu. if you're able, maybe try logging off and back on again. That seemed to fix the issue for Dr. Tan. And I want to thank our audience for your patience. Sorry for these technical challenges.
Hello, can you hear me okay?
We can hear you. Perfect.
Thank you. So sorry about that.
No.
Hi everyone. So apologies for the equipment smarter than user at this current junction in life. I'm Dr. Saskia Popescu, and today I am going to be discussing a little bit of global health security or insecurity and how we have set the stage really for a pandemic. And I just want to say thank you to the previous speakers for giving such detailed overviews, especially of the science. And my goal within this talk is to really discuss a lot of the critical infrastructure that has gotten us to this point. So prior to starting, I do want to provide a land acknowledgement. I'd like to take a moment of reflection to acknowledge that I'm speaking from a location in the traditional homelands of the Aboriginal and Torres Strait Islander peoples and representing an academic institution on the traditional homelands of the Manahoic and Anacostan people. While land acknowledgements are one small piece of disrupting colonial structures, it is important to understand the long-standing history of genocide and forced removal from these territories, and through such, work to honor and respect the many indigenous peoples connected with these lands on which I speak. So first and foremost, what is health security? This term gets thrown around a lot, so I want to just take a second and break down all of the vast components of it. First and foremost, it's really protection of health before and after epidemics and hopefully avoiding pandemics. But it's really how infectious diseases can trickle into so many aspects of our critical infrastructures and also translate to security vulnerabilities. So as time has progressed and our world has become more interconnected and more complex, we actually see more topics creating health security dynamics and vulnerabilities. And traditionally, I think people often thought this was bioterrorism, whether that is a state-sponsored bioterrorism event or a non-state sponsored, or a natural outbreak like a pandemic. Those were kind of a binary approach to this, but it really has expanded to include medical countermeasures, antimicrobial resistance, biosurveillance, biodefense, but also biotech and our bioeconomy. We are increasingly having conversations about the advancements in life sciences, like dual use research of concern and gain of function research that can use CRISPR-Cas9 or gene editing. And also, this includes a lot of the critical infrastructure capacity to respond to these events. So we know, and we've all lived it for the past 3 years, that infectious diseases like COVID-19 can be very impacting to our local, national, and global efforts and our lives, essentially. But really, I think often in terms of global health security, we really don't discuss often enough just how this feeds into so many aspects, whether it is trade, access to care, but also we're increasingly seeing things like misinformation and disinformation. More and more topics are coming up in terms of laboratory biosecurity and biosafety. So I mentioned advances in life science. Now, this is a topic so many of us are hearing a lot about in relation to COVID-19 origins, SARS-CoV-2 origins, and the dynamics and the biosafety, the biosecurity measures around research involving gain of function and especially involving pathogens of pandemic potential. So as I just threw a lot at you, you can imagine global health security and health security in of itself is extremely complex. It's constantly moving. And it's rather unique because infectious diseases are unique. Unlike some of the threats we often think about, like nuclear or chemical, these can evolve. There's multiple generations of cases. There's not just a very obvious defense and offense perspective, but there's a spectrum of biological threats and risks and vulnerabilities. And these have very serious implications for how we respond to them. So global health security really means an outbreak anywhere is an outbreak everywhere. You've probably heard that multiple times, but also that disease knows no borders. And I put an asterisk next to each of these because I think that these are important concepts and statements, but ultimately they fail to account for the fact that It's not necessarily true. There are countries and regions that are inherently more equipped to respond to infectious disease threats. We are not all on the same playing field. And I think a big part of this too is that, we think that disease knows no borders, but it does in some ways. There are security measures that are put in place. There are public health interventions that are put into place that make it harder for infectious diseases to travel to certain areas. We saw with COVID-19 a lot of efforts to quickly lock down travel to certain areas. While that isn't necessarily the most effective strategy, it is a way to slow certain things depending on the disease. But I think as we discuss how we got into the COVID-19 pandemic and what preventing the next pandemic looks like, it's really important to acknowledge that there is an inequity in terms of global health preparedness. And that means that we have to also consider that just because a country might be high income does not mean that they are inherently more prepared than a lower middle income country. This also really emphasizes the fact that there's a wider range of biological threats than we had 50 years ago. And in most cases, we refer to these in global health security as what we call a wicked problem. And that feels a little too on the nose sometimes, but that just simply means that it's a really complex challenge that is evolving faster than our capacity to manage it. But also, infectious diseases are increasingly becoming securitized. And, for a lot of these conversations around what that means and if it's a good thing, there's no perfect answer, to be honest with you. Global health security in of itself means it's become securitized, but I want to kind of take a step back and acknowledge that pandemic preparedness, biosecurity, biosafety have all become securitized. And while that means there's often an influx of attention and funding, that can also bring about a lot more scrutiny in areas that we hadn't considered, which isn't necessarily bad, but it does change the dynamics of the conversation and bring about that military component, the security component that these issues haven't previously had before. So I'm just going to be discussing one side of the spectrum, and that's really natural biological threats. But I do want to emphasize, throughout this talk that we are having increasing conversations about how preparedness isn't just about one of these things. It's about all of them. So natural outbreaks are unpredictable. There is a predictability in the unpredictable nature, and that these things happen. We know that they're going to continue happening. Emerging infectious diseases are increasingly becoming an issue. And I say that as someone who worked in healthcare during Ebola, during the first year of the COVID-19 pandemic. And, these are things that are increasingly obvious to those working in infectious diseases, but at the same time, for those working in healthcare and the larger society, they may not realize that infectious diseases they're not going anywhere. They are only increasing in frequency, and emerging ones, it's something that we've been struggling with for a long time, that really emphasizes the importance of One Health, because spillover is a very real issue. 70% of emerging infectious diseases are zoonotic or of animal origin. And our increasing encroachment in the environment and animal habitats is only going to increase that risk for transmission and spread. So antimicrobial resistance is also one. And I always like to emphasize this because as we discuss pandemics, I think we often really focus on things like SARS-1. We've discussed Ebola and a little bit of Zika and Mpox, but antimicrobial resistance is actually kind of this slow burning pandemic, if you will, that it's not going away. It's only getting worse. Things like Candida auris are extremely drug resistant and very challenging for us to not only treat, but also maintain surveillance on. And the thing that worries me so much with antimicrobial resistance is that it really stresses us in ways that are very economically burdening. And if you think about how we approach it, it's not just within public health and healthcare, it's also within agriculture. And medical tourism is a huge piece as well. So these are all of the kind of biological threats that we have to face. And this is just one side of the spectrum. And I think when we are discussing how we got to this point in pandemic response and what it looks like moving forward, we have to acknowledge that these are somewhat unpredictable events, even for diseases we have historical context with, like Ebola. We really struggled in 2014 and through 2016. And even now, I can't say that we would have a perfectly seamless response to Ebola should we have an unexpected case in the United States. And I think so much of that is really acknowledging that a lot of these diseases, there's a preconceived notion that they only impact certain regions, certain areas. And while we put a lot of funding, especially in the United States, into healthcare response and biodefense, if we don't deal with something frequently, we're really not prepared for it. And responding to Ebola, I remember being in infection prevention during this. Suddenly we were having to create policies for doing hemodialysis and labor and delivery. Even though we had all of this knowledge about Ebola, we had never actually put that into response within a highly affluent healthcare system, and one that with a lot of really exciting, wonderful medical capacity, but that actually increased risk. So response ultimately is lacking on the best of days. And response around a novel pathogen is a lot harder. We've all experienced that. The transmission dynamics, I think, are especially hard. And if you are experiencing a pandemic or preparing for a pandemic with quote unquote disease X or a novel pathogen, you are going to be learning as you go. It's that simple. We are building the bridges we cross it in some ways. And we saw this with COVID-19 when it came to transmission. Early on, there were conversations really focused on fomite transmission, environmental disinfection, because that was our historical context for SARS-1 and how we handled coronaviruses. As we learned more about that, so much focused on nuance and how do we address these complex topics that, yes, this is a respiratory pathogen. We have asymptomatic transmission and there are going to be novel variants, but we don't want to dumb it down too much. And the truth is that in so much of public health communication, and especially with COVID-19, we've tried to make it really simple because we felt that was a way that you could get the public to understand it. And that's really not the case. You have to be able to explain nuance. And this is something that we really, really struggled with in the United States. And I think just in science communication as a larger topic. Misinformation is increasingly real. We had jokingly the term is armchair epidemiologists, but people who really had never worked in or understand infectious disease epidemiology or just virology, suddenly having a lot of access to media and being a spokesperson for issues that they didn't really have the capacity or knowledge to answer. And unfortunately, that also translated to misinformation and disinformation and amplified some of the scientific debates on social media. So, part of this is also that it's a marathon, it's not a sprint. And while Ebola felt very short focused in 2014 from a healthcare perspective, at least, COVID-19 is a marathon. We're still struggling with how to kind of get off the wagon of acute emergency response and now walk the path of sustained infectious disease. We're going to be dealing with this for a while. So increasingly, there's also a focus on origin. It's a novel pathogen. We want to understand where this came from so we can address those vulnerabilities moving forward. Unfortunately, though, it's very easily politicized, and there is an impact on global response and cooperation as a result of that. And that often means that as we address novel pathogens, we have to build that process in much earlier. So there's also been a lot of public attention and monetary injections, which are great, but those are very momentary. We are starting to see so much of that kind of fade and wane, which means what does future pandemic response look like? And I just want to acknowledge, though, we do a lot in the United States. And this is, some of this is international and a lot of this is very focused on the US. But and this is a tiny, tiny drop in the pond of efforts to respond to infectious diseases and prepare for the next pandemic. Everything from the EIS, which is the Epidemic Intelligence Service, to the State Department's Office of International Health and Biodefense. There's the BioWatch program. In the Biological Weapons Convention, this is a UN treaty to ban biological weapons that also includes discussions around verification and surveillance. So we have the Global Health Security Agenda. These are all really exciting and important aspects of not only preventing the next pandemic, but acknowledging that we have to get ahead of it through biomanufacturing, through public health workforce and healthcare workforce, but also viral discovery. And, I included the Bioweapons Convention and BioWatch in here for a very specific reason. And that's because as we deal with a pandemic, whether it's a known or an unknown pathogen, there will be questions about attribution, meaning, is this natural, or is this, if there are indications that perhaps it is a biological event of nefarious intent or accidental, those will come into play. And I include this specifically while this doesn't apply to SARS-CoV-2. The Biological Weapons Convention really came into a lot of conversation in mid to late 2022 because Russian allegations of a joint US-Ukrainian biosecurity initiative that was going on. So a lot of our efforts to actually increase biosafety, biosecurity, and pandemic preparedness globally, can be misused for disinformation campaigns. But all of these nonetheless really amplify the fact that we are doing a lot of work. It's just that this is a really complex problem. So acknowledging the reality of a wicked problem, and these are just some of the examples that I mentioned before, but there's also, we will soon be reauthorizing the Pandemic and All Hazards Preparedness Act. We have the National Science Advisory Board for Biosecurity that was really created under PAFA. And so much of this focuses on addressing these advancements in life sciences, such as research with gain of function involving pathogens and the pandemic potential, and how we are infusing policy and regulatory oversight into that. And also the international health regulations and pandemic treaty. There is also within the WHO a scientific advisory group for origins of novel pathogens, or SAGO. And we are within the United States, especially acknowledging some of the gaps that exist. So the CDC has developed the Center for Forecasting and Outbreak Analytics. Again, this is just a drop in the pond. But these are ways that our historic efforts to respond to biological events and build that infrastructure for protecting and preventing the next pandemic. But some of them are also more recent, acknowledging some of the areas that we really struggled with when it came to COVID-19. And unfortunately, I think we can all appreciate, even when you're doing an exercise, let alone a real world event, some things you just can't plan for. Some things you unfortunately learn through, I don't want to say necessarily trial and error, but frankly, just error. And the reality is that there's a lot of geopolitics involved in this. And unfortunately, some hubris as well. And I mentioned hubris, and you'll see in the next slide, but there's this really common ideology that we assume wealth automatically translates to capabilities and capacities when it comes to infectious disease preparedness and pandemic response. And the truth is that it doesn't. We saw this with COVID-19. The United States, despite putting so many resources into pandemic response, really, really struggled. And in a way that I think amplified that we have a lot of work to do on a local and international level. So I like to include this particular quote from Ed Young of The Atlantic, because I think not only has he been a really wonderful science journalist in all of this, but this quote really hits the nail on the head. And that's, COVID-19 will neither be the last pandemic nor the worst. Its lessons will dictate how well the US prepares for the next one. And the country should start with its understanding of what preparedness actually means. In 2019, the Global Health Security Index used 85 indicators to assess how ready every country was for a pandemic. The US had the highest score of all 195 nations, a verdict that seems laughable just 1 year later. Indeed, 6 months into this pandemic, the index's scores had almost no correlation with countries' actual death rates. If anything, it seemed to have indexed hubris more than preparedness. And I do want to take a moment to acknowledge the Global Health Security Index is a really important initiative from a really wonderful team. And the goal was to understand vulnerabilities, but so often we don't really understand our vulnerabilities on a larger scale until we have to put them into practice. So how did we get here? And there's a lot to unpack. So first, we live in a highly interconnected, densely populated world in which our encroachment on and interactions with animals and the environment is only increasing. And it's really underscoring the importance of One Health, which is that relationship between animals, humans, and the environment. So there's a lot, and we could probably spend hours discussing exactly how we got to this point with COVID-19 and hopefully the lessons we will learn from it. First is a weak global governance in terms of prevention and response to global health emergencies occurring in sovereign states. And this really speaks to our expectations of the World Health Organization and global pandemic response. So without going too much into detail, I think the biggest kind of lesson from this is that many states, many countries felt that the WHO should intervene and should take a larger role, but the WHO is only as strong as member states allow it and grant that authority. So if you are a country that really wants autonomy, I should say, then, and you're not granting the WHO that authority, then it becomes an issue of, they can't really just come in and assist. So there's this kind of challenging response and expectation with global NGO norms, but also agencies like the WHO, but also states wanting that autonomy and that sovereignty, but not necessarily having the best relationships and partnerships when it comes to these things. So there's a cycle of neglect as well. The US has had decades to prepare for these things, and we've done a lot of important work, but we do see these trends, and you see on the right side. This is from a really great article within the Washington Post that focused on funding just for the hospital preparedness program. This is something that's very near and dear to my heart. And unfortunately, we felt this really severely, where you see this kind of roller coaster of funding when it comes to certain issues, and infectious diseases are not immune to this. So you'll get a surge of funding that goes into a topic. And then when public interest in that has waned, or we no longer feel that it's, an acute issue, funding drops. So this is really, unfortunately, the reality of so much pandemic preparedness and response. The latest presidential budget, for fiscal year 2024 is really emphasizing this and focusing on that. But it's going to take decades to really build up a public health, a healthcare, a research workforce to hopefully address some of these issues and these vulnerabilities. So there's also increasing biological threats and lackluster sustained response. It's kind of what I've underscored in terms of, we like throwing money at a problem, but not sustained funding. We have a lot of vulnerable supply chains. So one of the examples I like to share is that when I was working in healthcare, we got ventilators, emergency response. We were able to get through the national stockpiles ventilators for our patients. Unfortunately, though, there's often a disconnect with what we think emergencies require and what frontline responders need. These ventilators were great, but most of them came without filters, meaning that there was no way to actually use them without increasing the risk of spreading aerosols throughout the air. Some of them didn't have the plugs to even charge them, or plug them into the wall sockets. So those were tiny little things, and it just really kind of amplified the fact that, we put so much resource into the strategic national stockpile, which is really important, but are we assessing and working with our frontline response teams to say, is this the best tool? Is this the kind of the mask you want? Do you have the capacity to do fit testing even for it? So, that really plays into also healthcare biopreparedness limitations. As you see on the right, funding is all over the place and it's increasingly dwindling. But I think also healthcare workforces are not ultimately designed for sustained response at such a high level. There is a massive challenge with this. We have a workforce that is extremely fatigued. This is also a public health workforce issue as well. And why we saw increases of healthcare associated infections and antimicrobial resistance. You are experiencing a burnt out workforce in healthcare and public health, and people are leaving. Right now we are seeing actually a lot of layoffs occurring in healthcare. And part of that is that this is an industry, especially in the United States, that simply isn't designed to handle a marathon of a biological event. And, even looking at some of the funding in the very beginning, when hospitals were asked to put a hold on elective surgeries and, really try to keep floors open for COVID-19 patients, that was extremely costly. It was very, very stressful, to be honest with you, because you had hospitals that were so empty and we weren't getting the COVID patients that we were expected, but it was costing millions of dollars a week. So how do you reconcile that? How do we prepare and encourage infrastructure like healthcare to prepare for something that is going to cost them money, is going to be very, very taxing on them, and is kind of, a high impact, but in some ways a low probability event? There's also speedy vaccine development versus vaccine hesitancy and misinformation. And this is a real problem. We are still struggling with vaccine misinformation and hesitancy within the United States. And on a global issue, there's a lot of vaccine inequity. So this is something moving forward we're definitely going to have to address. But I think I also want to underscore the underfunded public health workforce. You know, I've spent a lot of time talking on healthcare biopreparedness, but our public health workforce is so woefully inadequate in terms of the resources they get. And I think the biggest issue is that people assumed when COVID hit, we could put a lot of money into public health and they'd be able to immediately respond, but that's simply not the case. Infrastructure that is required to respond requires us to give them time to receive the funds, search for people, hire people, train people, and then be able to utilize those people and keep them. Because if you have this constant cycle, no one's going to stay in there. And you then start losing them when suddenly the funding runs out. So now all of a sudden you have a large workforce of public health individuals burnt out and tired who are unable to find jobs. And that's very concerning, especially as we are only seeing an increase in infectious disease events. So there's also policy versus science. You know, travel restrictions that I mentioned, a lot of the changing guidance we saw, even from the CDC, without necessarily communicating the nuance to it, the whys to it, and that science sometimes is imperfect. So I think very, very early on, we learned really frustrating lessons that you have to tell the public, especially when it's around a novel pathogen. You know what? We don't know everything. Our knowledge is going to evolve and our guidance is going to evolve. And that's a good thing because that means it's getting better, but it's going to be an imperfect response. And we also have a lot of social vulnerabilities that put us in this position. You know, there is a massive disparity between vulnerable populations, between high income and low to middle income countries. And I also want to add too, science literacy and science communication is a really big piece to this. And that's not just in the general public, it's also in our policymakers. You know, there's a very significant gap and in the science education and awareness that those making decisions have. So why does all of this matter? Not only are we in a progressively interconnected world with growing incidents of outbreaks, spillover events, and securitization when it comes to science and response, but also infectious disease preparedness and response are increasingly politicized and impacted by geopolitics. So our efforts to build capacity from the development of non-pharmaceutical interventions to vaccines and addressing the gaps in public health require us to acknowledge these things, to acknowledge not just the securitization of this, but how politicized these topics can become. And to get ahead of some of those issues, to get ahead of some of the geopolitical issues, we have to build in some of these protocols and this sustained response, preparedness, everything much earlier on. So here are some of the questions that we're actually speaking to and some of the challenges that we're facing that I think will underscore a lot of what we need to address to prevent the next pandemic. So, these are questions that are currently happening in research, and you're seeing a lot of congressional testimonies about them, et cetera. But, should viral discovery, which some people call viral hunting or virus hunting, continue to occur? Do we need more regulations around gain of function research involving pathogen and pandemic potential? Who is responsible for origin investigations? And I know that's kind of ironic, me saying who, but is it the World Health Organization? Should there be a multilateral organization or group? Where should we put resources for pandemic response? How do we address misinformation regarding vaccines, but also non-pharmaceutical interventions? And have we addressed the supply chain issues for personal protective equipment? So these are just a handful of the questions, but I think really speak to the larger issues we are struggling with, not only in global health security, but how we learn these lessons from COVID-19 and build an agile response. Because one of the most frustrating issues we have when it comes to outbreak response and building pandemic response or biodefense, all of it, is that we often use the lessons learned from past events without building a certain amount of pragmatism and agility into it to be able to flex, knowing that even if it's a pathogen we are used to and we have experience with, it's going to challenge us in different ways. So the hardest part is acknowledging, excuse me, we're part of the problem actually. And that means, as I mentioned, using the lessons of the past without building some of this capacity to be flexible within them, to acknowledge, okay, so we didn't respond accordingly in this regard. what was the actual reason for that? Let's deep dive into this. You know, I think the origins conversation right now is a really big indication of this, because while it is important work and it needs to be built in so much more to early pandemic response, there's so much politicization and partisanship in the United States right now around this conversation, when we really should be focusing more on why did we struggle with response so heavily? Why was the United States really struck so significantly ill-prepared and struggled just to build in response within its critical infrastructure, despite having all of these resources? So we need sustained funding for all spectrums of health threats. And I think a lot of people, you know, there's a misconception that building public health isn't going to apply for something like bioterrorism. And if you actually build in a critical infrastructure of healthcare readiness, of public health, and build up that workforce, build up testing and biosurveillance and early warning and healthcare response, all of it, data infrastructures, excuse me, those will help you respond to every biological event. We also need to lean on the experts to help guide these discussions and these findings. And it's not just a matter of policy, learning and listening to science, but also science learning and listening from policy. We need to really engage communities and local leaders, because we learned so much from MPOX that, you know, we are struggling on a national level with that. And if you don't engage with your community leadership and so much of your public work or your public initiatives and your vulnerable populations, you are not going to get where you need to. And you know, the simple truth is that we've learned this a lot, but we're still struggling to implement it on a more long-term effort. So my hope is that MPOX will be a really big learning lesson for us moving forward. We need to ultimately protect our vulnerable populations and acknowledge those social inequities. So, you know, I mentioned the biggest debate we're having in the US right now, which is COVID origins. And what does that really show? So, you know, I just threw a lot at everyone, and I hope ultimately this shows that global health security, you know, pandemic preparedness, there is so much more work to be done, and it's extremely complex, and it's only getting more complex. So I just want to say thank you to everyone, and please wash your hands.
Thank you so much, Dr. Popescu, for that wonderful presentation, and really thank you to our whole panel for sharing your work today. I think we had a really broad scope of presentations from topic and also globally a broad scope. So thank you so much. I think that's really impactful. I'd also like to take this opportunity to once again thank our symposium sponsors, Sino-Biological and ACRO Biosystems. And now let's jump into our Q&A session. So just as a reminder to the audience, you can feel free to submit questions for the panel anytime, including during this Q&A session. You can use the tab on the right side of the screen. And the audience has submitted several questions already, so we can jump into that. And I do see that Dr. Kindrachuk has kind of answered some already, which is fantastic. Thanks so much. So we'll start with, there's a question from an audience member that really talks about kind of growing awareness of immunovulnerability and how that intersects with variants of concern and like long-term infections. So I wonder if maybe Dr. Kramer, you could speak to this first, you know, speak to that intersection between immunovulnerability and emergence of variants of concern.
Yeah, I mean, can you hear me?
I can, yep, absolutely.
I mean, that's a very important topic, right? Initially, when variants of concerns emerged, it wasn't clear where they exactly are coming from. There were different hypotheses. One was that the virus went into animals and then back into humans. Another one was that it's just, you know, gradual changes over time in the population. But one hypothesis was that these variants are generated in people who have infections for a long time because the immune system might not be able to clear the virus, right? And I think right now this is not just a hypothesis anymore. This is what we see. There is actually a lot of studies that looked at persistent infections in partially immunocompromised individuals. And we had one study here in New York where we found a patient who was infected with BA.1 Omicron for 3 months. Unfortunately, died afterwards, but that during that time 8 mutations in the RPD accumulated. Then this virus spread on to other patients and then was found in the community. And so this was basically a variant in the making, right? So the problem that I see right now is we don't have good protocols of how to treat these people and to make sure that that the virus is cleared, right? And so I think it needs clinical studies to look which combination therapy might be helpful for that, right? The other problem is this is something that we can do in the US and in Europe, but a lot of people globally have immunodeficiencies and cannot be treated. Maybe because the drugs are not available and so on and so forth. But there's also an underlying issue, which is HIV, right? People who have untreated HIV also have an immunocompromised immune system, and they might also have these persistent infections. In order to avoid that, it would be just better to treat them for their HIV infections, right? And then basically make sure that they are immunocompetent, and then it wouldn't happen. I see that as a huge problem, and I see that as a huge problem in terms of staying on top of SARS-CoV-2 variants. And I think we need a national and an international effort to solve that problem.
Absolutely. Thank you so much. Does anyone else on the panel want to speak to that question at all?
I'll throw my thoughts in. This is Jason. I think that Florian brought up some excellent points, and I think there's an aspect of all of this again that we need to appreciate, that when we're kind of viewing this lens of further variants of concern for SARS-CoV-2 or other viruses, we have to again think about this from the global perspective, right? And it becomes a question of saying, okay, what are the differences or the different things that are required in different regions of the world to address these issues. Trying to get access for antiretrovirals is critically important, as is getting access for basic health care in many areas of the world. So I think that there's a real complexity in trying to address all of this, because we're not looking at an equal playing field. But that also should kind of instill in people that we have to address it somehow, right? Not addressing it is just going to further exacerbate the issues we see. And whether it's SARS-CoV-2 or a different virus that emerges, or viruses that are already circulating, we need to start to appreciate what we can learn from the missteps, as well as the things that were done correctly through the COVID-19 pandemic, and trying to understand how to be able to move forward in terms of preparedness.
Absolutely. We can go ahead and move on to the next question. So there's a question about asymptomatic transmission, and how in the real world, how can we prepare for and counter the threat of asymptomatic transmission? Maybe we'll go to Dr. Popescu first, if you'd like to address that one.
Yeah, I'm happy to. And I just want to entirely mirror Jason's comments in the chat on that. I think, one of the biggest challenges we faced with COVID-19 was just the volume of asymptomatic transmission. And, early on we saw those, and I was definitely a part of it. And we were like, oh, you don't need a mask unless you have symptoms, because that's been traditional public health guidance. But the reality is that we are increasingly going to see these issues. So in terms of a public health response, I think so much of this is going to come down to screening, to rapid response testing and access to testing. And what made COVID-19 so unique is that we saw a diagnostic test used in a really unique and unprecedented way. So I think we've all probably experienced a situation where we tested to travel or tested to have a social gathering. This is a really unique event and situation. So part of this will come into play in terms of the prevalence of the disease, how common is it, and is it a high risk? But also if this is a pandemic, you'll likely see more testing, but we will have to really scale up testing and access to point of care testing and at home testing as well, and it's going to have to be pretty accurate, pretty sensitive, and specific too, because one of the concerns I think early on is when we were discussing antigen testing that it didn't have the same level of sensitivity as PCR testing. So moving forward, how can we prepare the real world? It's going to come down to testing, screening, but contact tracing is imperfect on the best of days. It really has a lot of, recall bias involved. So I think we are going to have to really ramp up the biomanufacturing aspect of that. And this is also really going to come down to access to tests, and that it's not just something, we mail a certain amount of tests out, to people, which is definitely a great strategy, but that you can easily and affordably pick up, or really in a perfect world get for free, because tests, especially in a pandemic, need to be accessible.
Absolutely. Thanks so much. Would anyone else on the panel like to address it? I know, Dr. Kindrachuk, I see your written response, but if you want to respond verbally as well.
Yeah, no, I'll just add a couple things. And, listen, I've known Saskia for a while. So Saskia, please just call me Jason. It still weirds me out when I see Dr. Kindrachuk with anything, because I'm the second smartest Dr. Kindrachuk in my household anyways. One of the things I do want to say is that, and there was somebody had commented in the question and answer area about the importance of bridging in social science. And I think that that's kind of one of the unmet areas when we think about infrastructure that needs to be brought in, right? Is not only this idea of, kind of brick and mortar buildings and access to testing, but also that aspect of being able to do community outreach in a transparent and respectful manner that addresses the kind of normal interactions within a particular region and kind of the customary interactions within a region, but also the aspect of community-based research. So, here in Manitoba, one of the things we have here, Dr. Rusty Suleymanov has a clinic that he runs or operates, which is based on community-based research, which brings in people from affected communities and actually has them participate in developing protocols and developing outreach activities and in kind of working in regard to addressing some of these issues. So I think that's another aspect that we need to appreciate is we need to build the infrastructure, but we really, really need to build those community ties so that people feel as if they are actually a part of the decision process, not just a part of the testing process and just a statistic in the end.
Definitely. Thank you so much. Yeah, more than just a number, right? Absolutely. So move on to the next question here. There's a question from the audience about, the benefit of developing treatment strategies versus prevention strategies. And, what's the more viable strategy, approach? And so I think maybe we'll head to Dr. Tan for this one first. I think you talked a little bit about treatment versus prevention. Would you like to speak a little more to this question?
Hi, about the treatments that I will actually more towards leaning towards the broad spectrum treatments for the viruses, and now we are actually leaning let's say there's the pandemics, and if you develop a vaccines that to target the viruses, that actually will take about 6 months and then or a year to develop the vaccines. And even if you inject into the arm of an individuals, it will take weeks to develop the antibodies. So there's a new concept that we are pretty I pretty like of this concept is use the antibody vaccines. So we actually, what we can do is we generating the broad spectrum or cocktails of the antibodies that targeting broad spectrum of the viruses, and we can use this as a front line to treat the patients or healthcare workers to block the infection cycle in the early of the outbreak. So it might be useful and to prevent the outbreak to become a pandemic in a sense. And while the vaccines while waiting for the vaccines to be developed. Yeah, that's all.
Absolutely. Thank you so much. Would anyone else on the panel like to speak to that question?
Yes, I think there are a few considerations, right? I mean, one is, of course, treatments might be available earlier than vaccines in terms of rollout, right? So, for example, if you think about the case of Hendra virus, right? There is an antibody that can probably be given. There's no clinical trials with that antibody yet, but you can give it as compassionate use to a person who came in contact with an infected animal or with Hendra virus in general, right? But it's very unlikely that a person would be vaccinated before that, right? So in some situations, you know, treatments are available and vaccines are not, or vaccines are not used. But even if you have a perfect world and before the virus even emerges, you know, you have a vaccine and then you roll that out and you vaccinate a large proportion of your population, there's still an important need for antivirals, and that's people who cannot mount active immune responses, right? We see that we have vulnerable populations. In our case, we have a cohort with multiple myeloma patients, for example, where a proportion of these people don't respond to vaccination and they stay vulnerable. And the only way to protect them is to put them on antivirals or to treat them very early with antivirals when they get infected, right? So either way, we need both options. Vaccination is usually easier and cheaper, and it's easier to prevent damage than to try to treat people who already have been infected. But in the end, we need both.
Definitely. Thank you so much, Dr. I think so. We also have a question that kind of discusses the hygiene hypothesis about, you know, whether it's beneficial to expose children to kind of farm environments or whatnot to develop their immune systems more, and, you know, whether this helps to reduce the spread of pandemics or whether this is kind of a foolhardy application of the concept of the hygiene hypothesis. So I might go to you first, Dr. Kramer, because I know you talked about wet farms in your presentation.
Yeah, so I grew up in the countryside. I had a lot of interactions with farm animals when I grew up. But I'm not so sure that just getting exposed to a lot of different microbes, we're exposed to them anyways, is going to do so much good in terms of protecting you from a pandemic virus down the line, right? There might be an interaction and an impact on how, if people develop allergies, things like that. But in general, I don't think that, you know, getting exposed to a lot of, I don't know, pathogens when you're, or animal pathogens when you're a kid, is going to prepare you for virus infection that might happen with a new influenza virus 15 years later. So I'm not sure that there's really a big connection there, except that, you know, if children are in contact with animals, there's always the risk that something jumps that can make them really sick, right?
Yeah, absolutely. Yeah. The risk might not outweigh the benefit there. Would anyone else on the panel like to speak to that question?
I'll throw in my 2 cents on this. Listen, I think that there's an aspect where we know that, you know, there's a certain amount of exposure to different pathogens that you know, can help with, you know, generating our long-term immunity. But we also need to appreciate that, you know, many of these diseases, unfortunately, certainly a lot of the ones that I've worked on or had the privilege of working on, have a disproportionate burden on those that are very, very young, right? And we see that with influenza, we see that with monkeypox virus, at least in Central African regions, and we've seen that with other infectious diseases. So I think there's an aspect which is there are some pathogens that you know, are helpful with generating, some immunity when we're younger, and certainly pathogens we're going to see lifelong with many additional exposures. But we need to appreciate that there are a lot of pathogens, unfortunately, that are out there that have very, very severe consequences, and in particular for those that are very young and very old. So we're still at a point of really needing to address how to decrease, at least from the zoonotic perspective, how to decrease those spillovers and realistically try to understand why those types of spillover events occur, because that's still, I think, where we're really at an infancy in understanding infectious diseases, and certainly the role of children in those infections.
Certainly, yeah. Thank you so much. We have a few related questions about kind of regional specific pandemic responses. And so I might go to Dr. Kindrachuk first for this one. If from a pandemic response perspective, especially from towards the beginning of COVID-19, were there any countries or areas whose public health responses really stood out to you for their response? Maybe a model. Yeah,
it's great, right? And I think that hindsight's always 20/20, right? So I think that there were things that different countries did that they did well. I mean, listen, I think we can certainly all talk about the transparency and data that came out of China, but one of the things that I think we saw very quickly, at least in Wuhan, was the implementation of a large scale containment or control strategy. Didn't work, and likely was not going to be able to work or be sustained based on what we now understand about transmissibility. But I think there was a responsiveness, and certainly there was an early kind of release of data saying that there had been these cases that were seen. I think that we need to do better in terms of that sharing. We've seen certainly from different countries. I think the U.S. did good with this from a diagnostic standpoint. We saw the sharing of resources and protocols and reagents across not only public health labs, but also academics who got involved in testing. I think Canada could have benefited from doing that. I think we had some impediments there. And of course, we also have to, I think, appreciate kind of beyond COVID, when we think about outbreaks, the human mpox outbreak in 2022 that's still ongoing. One of the things that I kind of continue to argue for is we actually need to be going to our partners that have been facing these diseases over and over again. So, our partners in endemic areas in Africa, we need to have greater reliance and certainly bring those voices to the table when we're talking about preparedness and response efforts, in particular with diseases that they've had a lot of experience with, to be able to help devise our containment control strategy. So I think that when we think about countries, I think, when we look at things like Ebola virus outbreaks, I mean, the DRC, Uganda, and moving into West Africa during the last Guinea resurgence or reemergence in Guinea, we saw very quick implementation of testing and contact tracing. Those types of countries, I think, are doing better and are actually now setting the precedent. So I think we need to certainly appreciate that being located in the global south doesn't mean that you are unable to address these types of events. In fact, we need to be looking at experts in those regions.
Yeah, absolutely. Thank you so much. Would anyone else in the panel like to address that question about kind of regional public health responses and preparedness?
Yeah, I can add some comments in there. I think to Jason's point, hindsight, right? I don't think a single country nailed response perfectly. I think some inherently performed a bit better. New Zealand is a great example, but there were also a lot of structural, geographical, policy-based decisions that allowed for low case counts and the ability to kind of lock down countries. I think the struggle that we're often seeing is that, each country responded and struggled in different ways. In the United States, we really were challenged with a lot of public health interventions and compliance with that and community sustained engagement with it. So when we talk about what countries performed best, I think the biggest question is, how do we measure that? You know, and that was one of the reasons why I really emphasized that, just because there's a lot of resources within a country, and especially put into, you know, health response doesn't always translate to capabilities and capacities. But I think really the biggest piece to this is acknowledging that no one got it right, but there was a very large assumption that high income countries that had a lot of the resources and didn't necessarily engage in global partnership. And, you know, I was really happy to hear Jason underscoring this. Like, we struggled with response a lot more than people realized. And, you know, even the countries that had the capacity to quote unquote lock down, you know, I look to Australia, their response then with vaccine rollout was quite delayed and very impacting. So more and more, I think we need to set metrics for how we discuss quote unquote success in these situations, but that we need to move away from who is the most prepared or who's the least prepared.
Yes, definitely. A more collaborative.
Maybe I can say something about the two, actually two things. One thing that I found very interesting is how, for example, South Africa approached sequencing and tracking variants even before that was a thing, and how well they did that, and how well they are engaging with their neighbors to actually bring these technologies on a routine basis to neighboring countries, and how that compared in a very bad way to the US initially, right? In the US, there was also a lot of sequencing in certain areas where mostly academic investigators were interested in that. But compared to South Africa, for example, the sequencing performed in the US and the number of genomes sequenced was very, very poor. And so this goes back to Saskia's point about it's not always the resource-rich countries that do a good job at these things. I think that's one important point that we saw with the variants of concern. But in terms of, I wanted to make one more general point in terms of pandemic preparedness. You know, there were efforts for pandemic preparedness before COVID-19. There were examples where the US, for example, responded very, very well to an outbreak. 2009 H1N1 pandemic, for example, the CDC was doing an outstanding job, right? Maybe not so much in 2020. And I would even argue that we are now in a situation where we are actually even less prepared to tackle a new pandemic. Not from a technology perspective. I think from a technology perspective, we're much better prepared, but from a society perspective, and this goes back to earlier points, right? Things like vaccines, measurements to cut down on virus circulation and so on and so forth, these are now very politicized issues, right? There's the left and there's the right, and they have very different opinions about that. That's not only true in the US. If you look into Europe, I would even say that there's more violent movements that are anti-vaccine, anti-countermeasures, and so on and so forth. And so I think with a new pandemic, it will be very, very hard to bring that part of the population on board and say, okay, but we need to do something and you need to comply. And I don't think it's just a trust issue, right? It's politicization of healthcare and politicization of pandemic preparedness. And this is a radical difference in the United States compared to before 2020, where basically pandemic preparedness was a bipartisan enterprise. And actually a lot of players might have been conservatives who took that very serious. And all of a sudden, this is a question of Democrats versus Republicans. And this is sad, and we need to reverse that. And we have similar situations in Europe. I think it's a very difficult situation. And my personal outlook on the next pandemic is very pessimistic, to be honest.
Yeah, absolutely. Something big has to change there, right? If we're for future pandemics, I think. There's another question here that talks about non-viral pandemics. So, you know, I think rightly so, a lot of our conversation today has seemed to focus on viral pandemics, but I'd certainly be interested to hear your thoughts on the potential of other pathogens such as bacteria or fungi. And I might go to Dr. Popescu first because I think you mentioned Candida in your presentation.
Yeah. So, Candida, a fungal infection, and I think there's been so much attention to fungus right now with HBO's series, is just one of those examples of a health threat that isn't particularly new, but has been worrying us for a long time. When we look at non-viral threats, I get really nervous about antimicrobial resistance. And part of this is my own bias, just having worked in healthcare for so long and seen the impact and the ease of transmission that occurs. But I think if there's a very real concern, when you ask a lot of people what keeps them up at night in terms of infectious disease threats, AMR is one for me because it's one that I jokingly say just isn't that sexy. It's not this emerging infectious disease that gets a lot of attention. It's the slow burn that is what is going to ultimately get us. There's been a lot of economic projections and just general projections actually about AMR, and that by 2050 it's going to be so much larger of an issue than we are currently experiencing. And if we don't get ahead of it, we risk that kind of quote unquote antibiotic apocalypse where we don't have treatment options. And the fact that, MRSA or methicillin resistant Staphylococcus aureus is now just this common skin bug that no one really worries about. There's even questions about, do we need to isolate patients in healthcare if they're being treated for MRSA anymore? So that's the point that we've gotten to. And I would say more and more, I think, we need to emphasize that, yes, viruses, and I defer to the brilliant virologists in this room on this, are extremely concerning, but we also can't, we have to be able to keep our eye on multiple infectious disease issues. And I think the fact that AMR and healthcare associated infections, which are often drug resistant infections, really increased so heavily during COVID-19 is a prime example of why we are so struggling to have a multifaceted response to infectious diseases, and especially those that test our antibiotic pipelines, test our capacity to develop new medical countermeasures, but also really rely on us to work across multiple industries. And that includes not just obviously healthcare and long-term care facilities, but also agriculture and trade. So, that's the one that I worry about.
Absolutely. Thank you. Would anyone else on the panel like to speak to non-viral pathogens that has the potential to cause pandemics? Okay. Maybe kind of staying on the trail of, pathogen specifics. We have a question about, bats as a species for zoonotic transmission. And it's asking specifically about influenza virus, or, I think probably could expand to other types of viruses. Are there specific bat species that are kind of a problem for potentially the next pandemic or epidemic? And I'll go to Dr. Tan for this one first.
Certain bat-borne viruses are only isolated on certain bat species. For example, for the SARS-related coronaviruses are mainly detected in the rhinolophus bat species, and for the Ebola-like viruses in the bats are mainly found in Rosetta's bat species. And I believe the certain bat species do carry certain viruses. Yeah, it really depends. Yeah, some alpha coronavirus can be detected in multiple bat species. Yeah, so but it really depends on how what are the host factors that are required for the virus to replicate inside the host, and I think that's what I know so far for this. Perhaps others panelists can actually comment on this.
I mean, maybe I can add something for influenza because I mentioned that earlier. In South American bat species, sequences for H17 and H18 have been found, but we don't actually know if they could transmit to humans and how dangerous that would be. What has been also recently found is H9N2 viruses in Egyptian rosettes in Egypt. And that virus seems to be relatively well adapted to mammals in general and could be a problem. It's not clear how easy it is for that virus to jump into humans in terms of the interface, but it seems to deal very well with human restriction factors and might also be relatively transmissible in mammals. So certainly something to keep an eye on.
And I'll throw in just a couple thoughts here. Listen, for Ebola viruses and filoviruses, we're always kind of focusing on fruit bats, right? There's, we've got good, not good evidence. We've got direct evidence for Marburg virus being isolated from fruit bats. For Ebola virus and Ebola viruses as a genus, it's been more complicated, right? We still haven't been able to isolate infectious virus from a fruit bat. But we have, serological data and partial genome sequences that give us a pretty good idea of the fact that these bats likely play a reservoir host role in transmission. And of course, there's been brilliant work that's been done where they've taken the geographic ranges of different types of fruit bats in West and Central Africa, and they've overlaid those geographic ranges with outbreak regions. And there's you can basically tease apart the 3 species that are likely involved. Or that overlap with those outbreaks. So it gives you a better idea of what's going on. But I think one of the things we want to appreciate is the more that we've been able to sample and actually do surveillance in bat species, the more we've identified, right? So Gabor Kemenesi's work with his group in Hungary, looking at Yovio virus, and which is another filovirus, and they've been able to identify is circulating in bats in Hungary. Doesn't appear to move over to humans, but certainly it should kind of imply to us that our perspective of where these viruses are circulating is oftentimes very much limited on where we've just happened to pick up outbreaks. So I think there's a real need for us to appreciate the complexity of bats. I mean, they're the second most diverse type of animals next to rodents. The role that they play in infectious diseases is pretty amazing. They're wonderful animals, but they just tend to harbor some pretty horrible viruses. And I think a big part of it is trying to understand how do we try and contain or limit those spillovers from occurring. We can't. We're not going to be able to vaccinate our way out of it. And we're certainly not going to be able to eradicate these diseases. But are there better ways that we can interact with people in communities that have close access or have a history of these types of transmission events, and try to better understand what is leading to these types of spillovers occurring, and how do we work with those communities to try to reduce the frequency of spillovers, or at least identify when spillovers occur as early as possible.
Yeah, certainly. Thank you all so much. I think that really speaks to the importance of animal experiments as well, which I think we had another question on as well. So that's great. We have a question that is kind of a big picture question about, what basic infrastructure is really needed for ideal preparedness. And I see that there's some excellent conversation in the chat already about that one. But would anyone like to speak to that verbally as well? Maybe I see that, Dr. Kinderchuk, that you addressed it in writing.
You're wondering if I want to expand, or could I? Yeah, I mean,
yeah.
Listen, I think Saskia gave some really great thoughts on this as well, right? There's an infrastructure aspect to this, as well as obviously, I think an integration and outreach perspective that needs to be addressed here, right? So there is this perspective from the work that we do in certainly in West and Central African regions, as well as the work of my department in East Africa, which is, the belief that we can just build infrastructure and that will solve all the problems. I think we have to appreciate, no, you need to build the infrastructure, but then there's a sustainability question, a training question, and also a trust kind of equation or question as part of this of, can you build up trust in the community to be able to help in utilizing that infrastructure. So, to me, it is a question of, listen, we can build more laboratory and clinical lab access in regions. Can we build up trust for the community to feel more inclined to be able to report when things occur or when they identify or somebody gets sick? Will they feel comfortable that there won't be stigma attached if they come forward and address these things? And can we also appreciate that many areas there's a pretty heavy colonial history that many people, including myself, don't fully understand and can't fully appreciate. We need to understand that historical perspective on why there may be some aversion to participating in this type of collaborative work or utilizing these types of resources. And that again goes back to this idea that infrastructure should also include the community outreach, community-based research type of perspective where we're working directly with communities. But I will say that certainly in West Africa, from the time that I was there in 2014 to the work that we do there now, we're still facing, or at least I see it as that those regions are still facing the same impediments that they had previously, which was, so there's a general lack of healthcare infrastructure. There's a lack of access to clean water. There's a lack of access for general living conditions and for food security. All of these things are exacerbating issues within the region for ongoing outbreaks, let alone brand new emerging diseases. So we need to appreciate this is not as simple as just putting up some infrastructure for doing diagnostics and that will help. It's a part of it, but there are some very, very basic public health things that need to be addressed critically.
Absolutely. Thank you so much. Dr. Popescu, would you also like to speak to that? I see that you commented on it in writing.
I mean, I think Jason nailed all of it. And I think the biggest thing that I consistently see is just this lack of sustained effort. And that's both, locally on a national level within the United States, but even our efforts abroad. We have a tendency of swooping in to support, but often once the acute issue is over, there's not a lot of sustainability. And I think that's really unfortunate because this kind of game of tag, if you will, almost with public health preparedness and really trying to ensure that we are building national and international cooperative efforts is clearly not working. I think COVID-19 has really shed light on that. And the hard part is seeing it kind of happen all over again. So I'm trying to be hopeful that there's, we all went through this really traumatic event and that we've all experienced it. There are previous biological incidents as, outbreaks of Ebola, H1N1. These were all things that I think many of us, we experienced in the peripheral. So there is a hope that the impact, both financial, both personal, both health, all of the above, will drive some sustainable change. But, a lot of it, especially in the United States, I think is being shifted to be more of a biodefense issue, be more of a health security issue, rather than, we can invest in public health and in lab infrastructure and surveillance and public health workforce, and all of those will support larger biological threats. So I think, as simple as it sounds, sustainability is probably the key issue that we struggle with. And that's a very complex problem that, that's why we call it a wicked problem. So I would put that as probably the biggest piece.
Absolutely. Thank you so much. I think that is a good place for us to wrap up today. I think really emphasizing that unifying aspect of what the pandemic has affected all of us globally. Thank you all so much for that fantastic discussion. And I'll repeat myself that we really appreciate your participation here today. And if anyone has further questions for our panel, please consider reaching out to the speakers directly. Their contact is shown on the screen. And just as a reminder, the symposium is going to be archived on the Scientist website. So you will receive an email notifying you when the recording is available, and you'll be able to find it there. Make sure to follow the Scientist on social media for any updates on future events. And thank you again to everyone who took the time to join us today, especially those of you who asked such insightful questions and shared some comments in the Q&A section. And on behalf of the Scientist, I'd like to offer an additional thank you to our panel, Jason Kinderchuk, Florian Kramer, Chiwa Tan, and Saskia Popescu, as well as our sponsors, Sinobiological and ACRO Biosystems. Thank you so much, everyone, and take care.
Thanks, everybody.
Thank you.